Good morning, ladies and gentlemen, and thank you very much, Pernilla, to give me the opportunity to open this final event of In2Track3. So, my name is Sébastien Denis. I'm Senior Program Manager in Europe's Rail. I will start with a bit of semantic because I'm introducing myself as a Senior Program Manager for Europe's Rail. You will hear a lot today about shift to rail. What is the differences? Basically, this is the same mandate, the same idea. So this is a PPP, a public-private partnership that deliver, thanks to research innovation, the future of the rail system. Okay, but why we have the branding Shift to Rail and why we have Europe's Rail is simply because Shift to Rail is somehow linked to the previous research framework of the Commission, so Horizon 2020, while Europe's Rail is linked to the next one, to Horizon Europe. So we have a small overlapping between the two. Europe's Rail officially has been launched in November 2021, so 2 years ago. But as you can see, we still have some projects running from the previous research program, and that's why to keep differentiating the two. The program we are talking about Shift to Rail for the previous one, the one that's been launched in 2015, while Europe's Rail is more used for what has been launched in 2022. Okay. So in which context are we now? So we are indeed as part of the Shift to Rail program. So In2Track3 is one of the projects of the IP3. And if I go for a top-down approach, so Shift to Rail has been created in 2015 with different IPs. So the IPs, it is an acronym for innovation, I even don't remember, innovative program, and they have been split in 6 areas. So the first one was for the passenger trains, so all development for subsystem for the passenger trains. The second one, more for the signaling areas, including also ATO, but also traffic management, etc. The third one, this is where we are today, so what is linked to infrastructure. Fourth one, what is linked to ticketing and IT solution. Fifth one for the freight. And we had a so-called cross-cutting activities. So what that was linking with transversal topics such as standardization, noise and vibration, smart maintenance, etc. So there are diverse topics that were transversal to everything. Okay. So the budget was quite significant. We had almost 1 billion euros, somehow shared 50% with European fundings and the rest coming from the members. Now, what was the idea of this, and what is still the idea of this PPP? So this is really to have collaborative research. So this is one of the P, so the partnership. So we are aiming to have the first P, so the private, so that is representing with some members. When we say the members, is the main actors of the European sector with infrastructure managers, operators, industrial partners, manufacturers, but also subsystem providers, and also research institutes, etc., university, etc. And we have the public that is represented by the Commission, okay, that is aiming to have some policy implemented. And we have the piece, the partnership, because at the end, this is really a win-win. So for the Commission, as I said, we have a tool to implement the policy, for example, the Green Deal, and you, as private members, you receive some benefit. You receive the benefit from the fundings, so some money that you receive from the Commission. You receive the benefit of having access to a network of experts in order to develop your solution. So you have in the same group, as I said, different actors, your future customers, the one that are defining the solution, the one that are somehow coming with the ideas, and you are all together from the very beginning to bring this solution to the market. And somehow you are mitigating the risk that this solution do not reach the market. And so in the specific case of the infrastructure, we are defining different blocks to reach this objective of having a more digitalized, a more automated railway sector. And we have been defining 3 clusters. So I will not go into the details of the cluster regarding the smart maintenance and the energy related, but more for the one that we linked to the project today. So this is somehow the TD1, the TD we have 1 to 3.1 to 3.5. So it was linked to anything related to switch and crossing, next generation of switch and crossing tracks, next generation of tracks, and bridge and tunnels. And this is all this activity that have been financed into this series of projects that you can see on the screen here on the bottom right. So with the blue one, with the members project, and in yellow and orange, the so-called open call. So in terms of organization in Shift Rail, we have a differentiation in call between the projects that were reserved for the members and the one that were reserved for the non-members. And the interaction was facilitated with different, I would say, legal framework, but we will see afterwards with Shift Rail we have a different approach. The results, I will not introduce myself. There will be the full day presentation about the different colleagues, about what has been, I would say, developed. But what is important to know is we are going to exploit these results in your field. So when I'm talking about exploitation, I'm not talking only about the physical result, about the product, etc., but I'm thinking also about the knowledge that you have been gathering during this first year. So when I say the knowledge, this is the success. So basically, when you are going to do further research on something similar or further development, you can, I would say, build on this success, but also what can be your failure. So basically, not to reproduce the same mistakes that you have been doing, because it's research innovation, it's normal to do mistakes, but it's important that we are capitalizing on these mistakes, not the mistakes, but the unsuccessful research in order not to do the same issues for the next program. And so I name here 2 of the projects, but it's mainly FP3 IM4L that is somehow collecting your results for further development. Now, in terms of organization, Europe is slightly different than Shift Rail. So same than for the project, we have also learned a lot from this 7th first year. And so we have slightly changed our organization. So one of the issues we have definitely see, it's that we were working a lot in silo. Okay, so IP1, IP2, IP3 with very little, I would say, interfaces and very little system approach. And that's why we have been introducing the system pillar. So the system pillar is somehow a new umbrella, let's call it like that, that the sector considered important to have to deal with any system consideration. So when I'm talking about system consideration, I'm talking about operational concept or system architecture. And so this system pillar has its own mandate, I would say, its own governance, its own budget. So the European Commission is putting 70 million euros on this single pillar in order to reach this objective. So I've been talking about the concept, operational concept and architecture, but associated to that, there is all the system requirement specification, these interfaces requirement specification, the functional requirement specification that are defined by the system pillar, and that will be at some point, I would say, integrated in the TSIs. Okay. And there is the maintenance of this architecture. So we have indeed a T-time solution, but it has to be maintained. We need to tackle the errors of that, and we need to take into account the future evolution. So this is the mandate as well of the system pillar. And finally, as you know, the rail sector is not working in a silo. It's fully integrated. And so we need to consider the interfaces with the other mode of transport. In parallel to that, we have indeed this innovation pillar that is somehow the correspondence of what has been done in Shift Rail with different areas, with much more digitalization and automatization ideas into the program, and also a support with the exploratory research. So we want still to, I would say, have ideas coming at float rail with, I would say, startups, university, research institute to bring new ideas that could at some point be taken into account with higher TRL into the program. And finally, and it's one point that has been discussed a bit yesterday, we have seen the need to have a deployment group. So when we have, I would say, demonstrating a solution at TR7, there's still a lot to do, and especially in terms of migration. It's not because you have a solution that will be immediately taken by the market. We need to consider the migration issue, and that's why we have been putting in place this deployment group. In terms of projects, as I said, we do not have the structure that we had in Shift Rail. So with one somehow research area split into several projects. We have also almost a one-to-one between one research area and the project. And consequently, we have much bigger project than in Shift Rail. You can see the values we're talking about. FP2 about automatization of the train operation. It's 150 million euros. So there is nothing like that in Shift Rail. Okay, and so we have split the research into 6 areas. FP1, somehow linked to the TMS and all the digital enablers. FP2 for the future rail operations, so taking into account the actual train positioning, ATO, GOA4, etc. IM4L, that is somehow, as I said, the next phase of the In2Track3 activities, mainly focusing on smart maintenance, so for infrastructure, but also running stock, but also the component and the subsystem development for the infrastructure. Rail for us, any activities regarding passenger trains, so somehow the mapping with IP1, the transformer project on FP5 with telematics and the digital decoupler for freight, and finally, future, that is linking a bit with all this technology, but with a specific market with the low density lines. The overall objective remains somehow the same. So we still are aiming to improve the performance, the capacity of the system, improve the punctuality, reducing the cost, and obviously to have, I would say, an harmonized approach and yeah, to reach the single European railway area. So this is still objective. It was the case of Shift Rail, and we are still aiming to have that. So to somehow to have the maximum of interoperability between countries and ensure that there is no barriers in the market development. So just for information, we have already developing our website. They have already some material that is available. So I really would advise you to have a look, because we are maintaining, I would say, up to date our information with news, the first results, etc. So this is on the EMAT website. And I would just like to take the opportunity of the 2 last minutes to present what is currently opening in terms of calls. So as I said, we do not have any more this concept of call reserved for the members and the one for non-members. This is now open to everyone. And this is currently open, a call for research and innovation for exploratory research. So it has been open in October. The deadline is February. We're just right in the middle. And so we are tackling different topics. So some of them are quite related to your activities, I guess. Some of them a bit less. But as I said, it is not restricted to members and non-members. So it's perfectly open to any consortium, either non-members consortium, either full members consortium, or a mix of members and non-members. So you have really the liberty to create the consortium as much as you want, Okay. And to go into the details, I just wanted to present 2 of them. So because there is somehow a link with our activities in In2Track3. So the first one is on the disruptive asset management solution, including urban use cases, is quite important. So here we give a lot of freedom and liberty of the use case that you want to present. There is some restriction in terms of topics. So for example, we don't want robotic development, but otherwise you have really the freedom to propose any topic in this regard. And the second one also somehow linked to the activities that has been developed in In2Track3. It's also another program. This is a noise and vibration topic. Here Again, I don't go into the detail, but talking various topics. So some of them is a continuation of the activities of U2L. Some other are tackling some other new concern, and also closing some point of the TSI regarding progress. That's it for me. So I will get to give the floor to Pernilla, and thanks again to give me the opportunity to open today.
Well, thank you.
Have a good conference.
Yes, my name is Pernilla Edlund, and I am the coordinator of In2Track3, which is the project that we are here today to have the final event for. I want to give you a brief introduction to the project. Some of you know what it's about. Some of you have been part of it. For some of you, it's entirely new, and you're just here to listen to what we have done. So I will just give you a very brief background on it. The project started in 2021. We are 26 partners from 11 countries, fairly evenly, in my opinion, spread over Europe, with some heavy weight in Austria and the Iberian Peninsula, which is nice. I consider us to be three groups of participants. We have the research institutions and research companies doing research, and universities who doing the background research, the more hardcore science. And we have the product development companies who have like a product they are trying to bring forward by using results and information within the project to take their products to the next level. And the third group would be the infrastructure managers, those who stand at the end of the line and want to buy these things that we take forward, and they want to have this to improve their infrastructure. And within In2Track3, we have all these three groups, and pretty evenly distributed as well among the members, about 1/3 of each. So I'd say that we have had good conditions for doing interesting research. And what have we done then? Well, we are the last project in a row of 4, 5, depending on how you count, but there are several projects before us. And we, through these projects, there is this increasing technology readiness level. So our research here and the development that we do in In2Track3 is based on what was done on lower levels in In2Track2 and in even lower in In2Track1, etc. So we build on previous work with the aim of having as many products as we can on a high technology readiness level, meaning that we have around 25 demonstrators that we have proven out as prototypes in operational environment, which means TRL7 then, which is as high as we can go. We can't go further because then it's a different kind of project, and that's not us. But still, we have 25 of those, and we have even 50 on lower TRL levels as well. So we are building, and we're also leaving behind, not behind, but we're pushing forward in front of us to the next projects, as Sébastien was mentioning, through most of it goes to IM4Rail, but it also in other directions. As an example, what have we done? Well, in the earlier projects, we've had, I'm taking the 3MB as an example. In the earlier projects, we have on the drawing table, we're measuring, we're calculating, we're making drawings, eventually building something to see what it looks like on site in the Acciona plant in Spain. And this is in the previous project. And then in In2Track3, wow, there it is, out in the field, in the on the iron ore line, being tested. And this is a picture from when the first iron ore train has passed it the first time. So this was a big moment for us, but that's just one example. And we have many of those examples that are out everywhere. And this is what our Visual Demonstrators Europe look like. And as I said, these are 25 of them, roughly. And meaning that these are things that you can go out into track if you could just go out into track, which you can't. But you think of it, if you could go out into track, you would see them. And you could have a look at them and really see what it's about. Probably some is missing here, but most of them are here. So what do we leave then? I was saying that we're pushing it forward. I mean, things are not done or ready or finished here in In2Track3. Work is continuing, it's ongoing, it's improving, it's being done better in other projects coming after us. So what do we leave? What are we pushing forwards? Well, I made some postcards for you to send off. And it's also a display of some of the results that you will see here today. Not all of them, but a few. Starting with the Atmo, we have improved noise and vibration conditions for grinding in urban environments. We have contributed to improved maintenance methods through the EMAT trolley. We have also contributed to a new type of smart material that can measure rail health through electricity. We have improved maintenance procedures for slab tracks by taking forward the 3MB. We have also taken forward a method for repairing slab tracks or separating rather slab tracks without the noise and vibration that it causes. We have taken forward a new repair method, discrete defect repair, with welding, and try that in track and see that it works well. We have taken forward an underwater rover for inspection of bridge fundaments and underwater inspection in general, and evaluation of that as well to see where we have damages. We have a new method for repairing brick-lined tunnels, which we have learned that we have many of in the UK at least, and I guess all over Europe. Yep. So this is a very interesting method that we can still, with the cost efficient and very promising results. Another area is tunnel drainage with the tunnel drainage rover, an improved way of cleaning drainage in tunnels, which is a complicated field, as we will see later on. We have also contributed to more improved repair methods through laser cladding, which we'll also hear more about today. We have contributed to taking forward a new tramway crossing, which is not tested out in field yet, but soon will be. So, and we have done a lot more than that, but this is just a snapshot. And you will get more snapshots during the day because today is all about snapshots. All right, how did we show this then? So how did we get the results out? Well, we've written 65 articles in the 29 different journals over the past 3 years, with quite a broad span, from plant health to geotechnics, over to wear and mechanics of materials and building engineering. So kind of wide spectrum, I would say. We have contributed to some people getting their PhD degree, and some other taking them further on the way to become PhDs. 11 of those, to be exact. And with these articles and with these PhD theses, there are a lot of conferences that we have been out on and presenting our results and sharing that. So the information has gone out as well continuously to many people who have seen our project. We have a YouTube channel where we collect the short and long, I should say, videos of what we have done. There are many nice short videos of 3-4 minutes just displaying a specific topics and how we have solved that and why is this a good thing. So that's something to check out. We have our websites. We have 2, soon we have 1. But displaying the results, showing the people behind it, who did this, and using that on our LinkedIn channel to spread the results. and to link that to LinkedIn, which has given a great audience. We have over 600 followers now on our webpage, so we know that the message is distributed, it's coming out. We have made 3 webinars on different topics, which have been very well visited, very well received, many questions, and very relevant and interesting questions. So it has also reached the right audience, so to speak. The people who we wanted to reach, well, we have reached them pretty well. And as a last piece, we are making a book, a concluding technical report, which is the same pretty much as today's, short snapshots of what we have done in the project collected in a book, more or less. And it will be distributed in March. And today's program, you have it. It's been distributed to everyone. I will not go through it in detail. I would rather that we have 1 or 2 minutes before we start with the first session on control. So the first one is control. How can we improve the assessment of the status of the railway? How do we detect and categorize faults? How do we ensure that operations are safe? The idea behind the presentations today, the 5 blocks that we have, is that is like a chronology, so to speak. We have an infrastructure, we try to monitor it. What do we do when we fail or when something happens? Shouldn't say fail, but when something happens. So that's the idea of today. That's the pathway for today. So the first is control, where how do we control our railway? And then we go on to how do we repair it? If something happens, how do we repair it and continue? So that's the idea behind today's presentations. And we are now 2 minutes ahead, so let's just take a 2-minute break before I give the word to Jose on the first topic here. So 2 minutes. Thank you all. No. No, you shouldn't.
So good morning, everyone. My name is José Solís, and I am Transport Infrastructure and Digitalization Manager at the R&D Department of CEMOSA. And today I would like to introduce the developments that we made within the In2Track family of projects, and that finish in In2Track3, as Pernilla stated. I will start with the challenges that we addressed. So, well, as all of us know, we have large numbers of rail infrastructure that are currently close or beyond their asset life cycle and need maintenance. There's also a pressing need for new methods to inspect, monitor, and assess rail infrastructure. progressing towards predictive maintenance. And these new systems generate large volumes of data that has to be handled and then analyzed in order to assess the state of infrastructure. So today I would like to provide two quick snapshots of the two developments of CEMOSA within the project. And the first one is the development of a bridge inspection ROUV, remotely operated underwater vehicle for infrastructure inspection, including several sensors such as cameras, water quality sensors, gripper, a sonar, and several extra navigation support sensors. This system has been demonstrated in several locations, including the dam in Rules in the area of Granada, the ports of Malaga and Marbella, and also two access bridges to the port of Malaga, one roadway one and one railway one, focusing on scour and debris inspection. In this respect, all of this information has been summarized into inspection guidelines and best practices in order to perform this type of underwater inspection actions. The second set of results that I would like to present today is related to the Sandbox platform that we have developed. This is a digital twin asset management platform, in which we follow the following concept for digital twin as a BIM GIS environment, enabling the integration with static and dynamic data and providing the ground in order to perform visualization, prediction, and simulation actions. In this respect, we have developed a robust data management system integrating information such as the one from the ROV, but not limited to it, also UAV information, traditional inspection information, etc. It has an interoperable architecture with a focus on analytical use cases such as operational model analysis on bridges or pavement degradation. And everything has been integrated into a modular asset management platform. The platform has 4 different services, including management of assets and inventory, inspection, including information on field visits, pathologies, and point clouds, monitoring, retrieving data from IoT systems that then is analyzed for operational model analysis, degradation of bridges, etc. And last but not least, planning, which is an area, planning of maintenance, which is an area which is under development. I would also like to talk about the future work on this topic. So with respect to the inspection ROV, this has already been incorporated into CEMOSA's portfolio, although further improvements are being considered in terms of computer vision. But we will also be working on the project that Pernilla mentioned, I Am for Rail, from the Europe's Rail Joint Undertaking, in which we will be working on 2 main use cases. The first one is the development of a bridge digital twin for a bridge in the Madrid-Valencia high-speed line, where we will be monitoring the bridge and providing operational model analysis on the bridge and analyzing the fatigue on the pod bearings. And the next use case is related to the development of an earthquake digital twin in the Palencia-La Coruña conventional line, where we'll be performing data fusion and we'll be evaluating the condition of the asset. All of these will be integrated into the Sandbox platform that I presented. So thank you very much for your attention, and I will leave the floor to the next.
And then we have Quentin online.
Yes, thank you, Pernilla. So I am Quentin Mayolle, a research institute in Raleignium, Rail Research Institute. So I will present today the work we have done in In2Track3, and I am very glad to present this. So our objective was to study surface defect with non-contact solution, here EMAT solution. So today is mandatory to follow the cracks. So here we are talking about squat and head check at the early development stages to follow the evolution of cracks. It is mandatory because maintenance operations are very costly and heavy. We are talking here about milling and grinding. So we want to detect a check and squat at the early stages to follow the development to design optimal maintenance plans. EMAT stands for electromagnetic acoustic transducer. This is a non-contact solution that is used to detect without any need of couplant or contact between the sensors or the rail to detect defect. It's a magnetic solution that generates ultrasonic wave, here Rayleigh wave that are surface wave that propagate at the surface of the material. The interest of EMAT has been demonstrated in In2Track3 where we had laboratory experiments showing that we can detect a check with this kind of solutions. The next step was to use this kind of technology in field, so with very complex environments, noisy environments. Next slide, Pernilla, please. Thanks. So what we have done in the In2Track3 was the design of a demonstrator trolley that will be used in field so it was a motorized trolley that could reach speed up to 12 km/h. First, the mechanical part of this project was to design and manufacture this trolley. We wanted it to be dismountable and transportable by human persons to be efficient on operated lines. Next, we also wanted to have a secure control of the distance between the EMAT sensors and the rail. So we had to put all the different sensors and actuators and to control them with a loop of software to be sure that we have a constant distance to adapt different geometries of rail. We also made this trolley remotely controllable by a human operator for security and for efficiency questions. Last of all, one major issue was also to face noise, measurement noise, electrical disturbances that are mandatory in field situations. So we designed new signal processing tools that will cope very important noises, combining new time frequency representation with wavelets and machine learning algorithm to be able to detect defects at check and to characterize them. We wanted to give some information about severity, in-depth penetration, and orientation of the quark. All this material has been tested in field in Getling's tunnel with a very complex environments, constraint of temperatures and dust. All the result was that we validated the demonstrator trolley and were able to detect a check in field conditions. The next step for this demonstrator trolley will be to gather more data about a huge variety of defects to be able to increase the efficiency and the robustness of this technology. We wanted also to increase the speed, to do not require only one human operator, but to have a remote control with speed up to 200 km/h. The last point will be to use other kind of technology because we only concentrated in In2Track3 on technology like EMATs, and we wanted also to include technology like eddy currents or classical piezoelectrical transducer to study not only surface defect, but also in-depth defect in the head of the rail, but also in the web or the foot. All this will require a fusion methodology to gather all the different information and gather all these things. There is a small video if you need to show the demonstrator in action, and we have also included one link to the publication. Thank you very much for your attention.
Thank you. And that video is also available on the YouTube channel of the project. And I should also say that all these presentations will be made available to anyone after today. So please, next speaker.
Yep. Good morning to everyone. Michele Maglio, currently working at Trafikverket, but in this presentation I will show some results obtained by me and my supervisors at Chalmers University of Technology on behalf of Trafikverket regarding the influence of wheel tread characteristics on the operational lives of the rail and the running gear. the main challenge that we had addressed was related to wheel tread damage. It's a common problem in countries which have a very harsh winter climate, like Sweden. And here you can see some forms of wheel tread damage that are quite common. For example, wear, wheel flats, or rolling contact fatigue clusters. Damaged wheels generate higher impact loads on the rail. And these higher loads can generate higher noise levels, but can also lead to failures of both the wheelset and the rail that can cause delays and extra costs or even accidents. The research we have performed on tread damage has been based on both simulations using an in-house software as well as full-scale field tests. This is an example of a simulation that was performed with our in-house software. And you can see here the damage is exaggerated, but when the damaged rail at point 3, the damage approaches the rail, then the contact force between the wheel and the rail goes down. Then the wheel is pushed downwards by gravity and the rail is pushed up by inertia. And at point 4, then an impact with a significantly higher force occurs. In In2Track3, we've also measured stress spectra for wheelset axles. In collaboration with SJ, the Swedish train operator, and Lucchini, a leading wheelset has been instrumented with strain gauges that can measure bending strains. Bending strains can then be transformed into bending stresses, and we have collected the frequency with which these bending stresses occurred on different stretches of the Swedish network. Here you see 2 examples, and you can notice that for one of these stretches, we have higher stress amplitude values, as well as a different shape of the spectra. We have modeled our spectra using 2 probability distributions. And by comparing the measured stresses with the track data from Trafikverket, we could notice that some specific track components, for example, switches and crossings, can influence some of the parameters of these distributions, as well as the stresses are very sensitive to curves and the track surface quality. Knowing the stresses that wheelsets suffer by running on different types of track, we could estimate the fatigue life of the axle, and so we can optimize the maintenance intervals. And this was performed in collaboration with SJ. We've also used wheel rail impact load detectors in our research in collaboration with SJ again and Trafikverket. And Green Cargo as well. In this part of the project, we have identified some damaged wheels that were running in Sweden and that were causing higher impact load levels. These wheels have been scanned by means of 3D laser equipment. And then their surface has been post-processed and used in our in-house simulation software. The simulated contact forces have been compared with the results from the impact load detectors. We could thus validate our software, as well as use the simulated loads to compute the fatigue stresses on the wheel and the bearings. Future work might be performed on the topic, so we can analyze even more the stress spectra and predict this, the track characteristics from the measurements on the train. And this could help the infrastructure manager to optimize maintenance plans. Simulations can be performed for a wider range of operational cases, such as running on curves or switches. And finally, different axle and wheel designs and their effect or impact loads and fatigue life and maintenance can be assessed. This is all from my side. Thank you for your attention.
Everyone, I'm Andrew Brown. I'm a principal engineer for tunnels at Network Rail, and I want to talk to you about subsurface tunnel inspections. So I just wanted to talk about some of the risks posed by railway tunnels built mostly in the 1800s. In the UK, these tunnels are largely brick lined, and unlike tunnels built in modern times, it's difficult to see what is going on behind the lining. We have nearly 700 of these in the UK. On this slide, I've highlighted just 2 failures that have taken place due to this problem. There have been many more. Virzy Tunnel, 1973 in France, following a collapse, there's over 100 fatalities where a train travelled up the spore heap and another train travelling in the other direction also crashed into the first train. More recently, a collapse occurred during works in Scheiberg Tunnel in Luxembourg, 2022. Fortunately, no one was hurt, but the tunnel was closed for a year, causing what I'd imagine to be enormous disruption. There have been many similar failures in this time, but over this time scale, but I've highlighted the worst and the latest. No doubt in both cases, ground investigation that was undertaken was deemed sufficient, but identification of all risks during the ground investigation of these tunnels can be very difficult to get right. In the top right of the slide, we can see an example of behind the tunnel lining. We can see how fractures in the geology can cause a failure in the rock. This wedge block failure might have already happened. We don't know about it, and through asymmetric loading could be causing a risk to the tunnel. Bottom right, we can see an example of how rock is being supported on the back of the lining and load transfer is occurring through these pillars, causing point loads. Brick arches don't like point loads, especially when they're 150 years old. These are risks we need to know more about across our tunnel portfolio. So when trying to see in or behind the tunnel lining, many methods are used to try and form an holistic picture. Ground penetrating radar, GPR, is one of those techniques that is widely used. The data is collected in small strips, so the technique is very access hungry. And as you can see in the top left, outputs are very difficult to interpret. Special input is required. Then the submitted report is highly caveated, meaning the data and therefore the risk remains subjective. Tunnel Subsurface Inspection Radar, or TSIR, combines the technology from airborne radar and conventional GPR and can deliver a 3D scan of the tunnel lining, showing voiding in and behind the tunnel lining that may have occurred. The outputs can be seen in any direction. Top right, you can see a cross-section of the tunnel lining, also with a few labelled possible defects. Bottom left, you can see the outputs, and you can see it in both planes. This allows the user to better understand the risks that are present behind the lining, allowing proactive interventions, helping to avoid failures, making for a safer and more reliable railway. In terms of future work, currently we have an assurance piece of work that's been undertaken by a leading consultant. This is looking at the future compatibility with existing tunnel risk data and the best use cases of the technology. From a practical perspective, monitoring of volumes can be conducted, for example, during grouting operations. We can use this data to help evaluate the holistic risks to a tunnel and to form future strategies also. User-friendly software, as we can see down there on the bottom right, allows measurements of voids and excellent visualizations. Other use cases can include retaining walls, culverts, brick arches, and track renewals. Thank you very much.
Thank you. Oops.
It's a different presentation. Yeah. No.
No.
It was different. Yeah.
No. There you are. My bad.
Oh, don't worry. Hello, good morning. I'm Reza Allahvirdizadeh from KTH, and on behalf of my colleagues, I will present briefly what we got to do in improving the design philosophy of dynamic design of railway bridges. We have focused on run and safety criteria, which is indirectly controlled currently by design regulations, controlling the vertical acceleration of bridges. This current criteria is obtained from a set of limited shaking table tests have been conducted in Bonn, where they concluded that when vertical acceleration on bridges goes beyond 7 meters per square second, probably we will have ballast instability. Our aim was to improve this design philosophy, so we needed to tackle this problem from two perspectives. One was how we can improve the current one to have safer designs, because as we understood, no probabilistic or safety-related analysis have been conducted when they proposed this criteria. And the other one was that, okay, whether this criteria is a good criteria or not. Regarding the first perspective, I mean, taking the criteria as it is and then improving the design philosophy, we could have followed two approaches. One was use probabilistic methods and particularly reliability-based design optimization to propose minimum design criteria. I mean that we optimize minimum required mass and stiffness for our bridges in a way that the probability of having an unsafe system is below the level that we desire. In that case, we don't need to conduct dynamic analysis in this context anymore. We can follow our design approaches, and then we check them, the two figures that you see in the below, the mass and the stiffness of our bridges. And if they are more than what is proposed in this approach, then we are safe. It's guaranteed that we are safe. Other approach is the one that all design regulations probably use. They use partial safety factors. Currently, the value that we use in this context is 2. But following partial safety calibration methods, we came up with new values that we can actually use 1.38 and then increase the design acceleration from current 3.5 meters per square second to something around 4.4. So it was quite big improvement. But in the next step, we need to see that, okay, can we improve the current design criteria or not? There are some uncertainties that have not been taken into account. One of them is probably about solid structure interaction effects, that there is extensive uncertainty regarding that. And if we consider that, like the figure on the left, we will have a fuzzy system, then we will have an interval of safety. And in some cases, we may end up, solid structure interaction effects are beneficial, and in some cases not helping the system anymore. So we need to take them into account. And on the other hand, we did some preliminary investigations, and we noticed that the way that we see the problem right now increases the epistemic uncertainties in our system. We know much less than what we believe that we know about the system. And if we take into account such effects, we will see that the probability of failure can be much higher than what we expect. So a set of new dynamic tests have been planned to be conducted during I'm4Rail project. That preliminary studies have been started, and they will be done in future as well. That was all that I had for today, and thank you for your attention. I hope that I didn't talk too much fast.
No. We have our next speaker, Anders Ekberg.
So good morning, everyone. I will talk about work done by me and mainly by Elena Cabo about track buckling, and looking out the window, that seems like a relevant problem. But don't worry, there will be a summer eventually. So what happens when it gets warm? Well, the rail wants to expand, but rail can't in a continuous welded rail. So you get compression, or in the jointed track, if the joints are close, you get compression. If the compression is high enough and the lateral resistance small enough, you get this buckling effect, as you can see here. To complicate life, what counts as a track buckling varies between countries, so comparing statistics is a bit tricky. But the main issue here is, I mean, in a way, it's simple. If we know the compressive forces, if we know the lateral resistance, problem solved. But how do we identify the critical sections along thousands of track kilometers? How do we know this is a critical position for track buckling? So what we've done in In2Track3 is to quantify the key parameters in terms of an equivalent temperature. So we know that curves are dangerous, more dangerous than straight track, because it's easy to buckle. But now we can say that one curve like that, that's equivalent to 20 degrees warmer temperature, for example. And that means that you can compare different factors in the same amount. We also checked between the experience-based quantifications that you have today and this equivalent temperature increase to see, okay, current guidelines compared to what we say, are we on the right limit? The equivalent temperatures we used in numerical simulations, and we also use statistics on track buckling events to find those. Looking on the case study, this is an example of a rail buckling outside of Gothenburg, where we can calculate an equivalent temperature as the current temperature plus an addition for curving, plus addition for poor ballast support and things like that. So what we see is that if you go about over 50 degrees Celsius, this is the Swedish conditions on that track, we see that all the cases on that track that got buckling were above that. So then you can start to be a bit careful. We also found some other things, that the influence of fixed points, like switches and crossing bridges, is quite small for all welded tracks. And that, of course, maintenance is crucial for preventing track buckling, because you increase the lateral track resistance. So what do we continue with? We continue in IM for rail, and we're going to enhance the numerical model and extend the parametric study to get more ideas. It turned out when we compare to the field studies that the data you have, data collection incident reports, that can need a bit of improvement. It's very difficult to connect the reports to what actually happened and where did it actually happen. We're also looking at planning maintenance action and quantify, okay, if you do this maintenance actions, how much better does it get? I think this also will facilitate standardization, since you get an objective quantification of how bad is this situation, in terms of that everything is counted in temperature. And you can also, I think, do some work with standardizing definitions and reporting on track buckling. And preferably you will be able to compare situations in different countries, which is very tricky today. So that was that on the track buckling. Thank you.
And now I wonder if Tobias is online, because we have indications that he is not. If he doesn't show, Thomas, where are you? Petrasek, there you are. Can you do this for him?
May I ask you maybe to reshuffle the program, because I don't know the
No.
slides. I can do it, but just have to see the slides.
Huh? Is Vesna here?
Yes.
Vesna is here? Okay. Vesna is here, so she...
Okay. But I can do, but
Vesna, we haven't tested this with you before, but would you like to jump in instead of Tobias?
She will, but I must make her representative first.
Okay. This is okay. I mean, we have one presentation left.
Okay, so now he is here also.
Okay, Tobias is here. We have one presentation left before we take a break. So there's no worry here regarding the time schedule, so it's fine. We wait for Vesna or Tobias to join.
Tobias is coming.
Tobias is coming. That's great. Let's keep it like this then.
Hello.
Hi, Tobias.
Hello. Hi. Sorry, as I wrote you, I have a different meeting at the moment, so sorry. But nevertheless, everything should work. Yes, I will give you a short overview of the work we have done regarding the monitoring of tunnel drainage systems. So next slide, please. In our railway tunnels, we have scale deposits made of calcium carbonate in the tunnel drainage pipes. This is a problem you have in almost every tunnel of the world, made of concrete and with drainage pipes. And it's necessary to clean these pipes about twice a year to avoid an increase of water pressure and a possible damage of the tunnel structure or a water ingress inside the tunnel. And at the moment, we can detect the condition of these scale deposits by camera inspections only, unfortunately, because this requires a track or a tunnel closure. And this is a massive restriction of the train operation, and nobody is happy because during the inspection time, we can't earn money because there is no train operation. Therefore, we have a huge interest to do more of our inspection and maintenance from outside of the tunnel. So this is in all our projects at the moment, the goal. And here is our goal, the remote detection of scale deposits with as low operational restrictions as possible. Additionally, we will get data for predictive maintenance. So at the pictures of the right-hand side, you can see this typical scale deposits made of calcium carbonate, and in the lower picture inside a tunnel drainage. So next slide, please. To solve this problem of the inspection, we worked in In2Track3 on a tunnel drainage rover, the prototype. The abbreviation is TDR. But I have to mention that we work on this topic since 2016. Because it's prototype design and construction, and there you need several years until you get results. So the prototype we built in In2Track3, it's you can see it on the right-hand side in the upper picture. It's waterproof because it works inside an environment with lots of water, and corrosion resistant. It drives at the moment more or less autonomously, or it can be remotely controlled. When we made this presentation, the estimated travel distance was about 10 kilometers inside drainage pipes. Now you will see in the next slide that during the last months we got results that now the travel distance is much more higher. It has an incorporated camera and a light source to get images of the drainage pipe. And well, we have some other features like an inductive contactless charging or so on, or the whole communication. We tested this prototype in the testing center of the Zentrum am Berg. This is an active iron mine in Austria, where the Montan-Universität Leoben built a road and a railway tunnel just for testing purposes. So the next slide, please. So luckily, it was possible to prolong the active part of In2Track3 until the end of this year. And so we were able to do some of the so-called future work on this topic. Nevertheless, we know that we have to continue our work during the next years to get to our final goal that this robot will work in that that we can use this robot really in our so-called drainage market or something like this. So here is an outlook of what we will do in the future, or what we have done during the last months, because then we had to finish the presentation. So we increased the capacity of the battery. So this is already done, and now we know that we have a travel distance of about 15 kilometers inside drainages. So this is really a great. It's really great that we achieved this. We will try to reduce the charging time in the future. We will add an additional track that the driving will be much better in the drainages. And what we also have done during the last months is to adjust the height so that when there is lots of water inside the drainage, that TDR can't be flushed out. The next really huge step will be a development of the software for autonomous driving under railway traffic conditions, because this is really something different from, this is really something that will be special. And of course, we will do lots of long-term tests inside tunnel drainage environment. So now I'm at the end of my presentation. If there are questions, I can answer them.
We take all the questions. Yeah, we take all the questions in the chat. So, and we will answer them after this meeting today.
Okay. Okay, so that's good.
If you have questions, just post them in the chat, please. Thank you very much. And now we have a short break, or long break. So I will leave you who are online, and I will ask you who are here to stay for a few seconds while I have a few words for you. So everyone, it's 10:45 and we move on with the presentations from today. We have, as I said before, for those of you who were present, we have 5 blocks covering different aspects of how to monitor, control, and maintain the infrastructure. Now we have now come to block 2, improve design. How can we improve and change the design of the railway in a sense to make it more durable and more lasting? So our first speaker, please, Andreas.
Thank you. I'm here to speak today about laser cladding and heat treatment of rails and switch rocks. Yeah, and now we have to look about the current situation. The current situation, there is no repairs on rails, but in Austria, they repairs some parts of the switch rocks in the field. Yeah. Now it's every time more and more increasing the wear, and also it's then important also that the when wear increase also noise, and when noise increase, they all have problems with them, and so for future we have also to get more rail transport, and so the lifetime go down. And also wear go higher. And for the future, we have to look about new maintenance for repair some parts for rails and switch rocks, and to make it more cost efficient. Here I want to show you the equipment we built up for rails and switch rocks, the complete equipment. At ACT, some movie. We weld on a rail, also on the switch rock, and so we have to choose the chemical composition. Chemical composition are very important because they have influence on weldability, all-in contact fatigue, and wear behavior. And so we have also to build up all the test rigs, and also to design samples to test the different chemical composites of material what we want to weld on a rail or on a switch frog. Yeah? The goals are to have a higher lifetime, yeah, and to make more benefits for outside. When we have higher lifetime, we reduce also the noise for the future. Yeah? And when we have positive tests, as we find some good chemical composites, we also have to put this out in the field. And for the field, we have to move all the results from the laboratory on a mobile laser. There you can see here some field tests on a switch frog. There we repair some parts where was pitting before. We weld this at the field at ÖBB. Yeah. And for the future, we have to make it better, because to have more power, to have more welding rates, to have more grading rates. Yeah. Also, that you can see here the difference between this is what we use in the field and this is now the future. Yeah, at this time when we make the field test, this was not completely finished from this company. Now it's already finished, so we can make the next tests also with the high power laser. Yeah, more automation, so we can look here. We built this by themselves to get the geometry completely and to put out the geometry in this machine to weld completely automatical. These are more in the future, and the next tests are coming soon. And yeah, to have these benefits very soon in the field. And from the last weldings at the field, we control that every month. And we see also what we see in the lab, that the lifetime is much higher than with the old one maintenance, than with the old maintenance with electric electroden welding. Good.
Thank you.
Hi, I'm Alfredo from Acciona, and well, we work in the fatigue capability improvement of railway bridges. Those bridges are still bridges in UK. We had a demonstrator in UK. You can see the connection between the bottom cross beams to the main beams. That's a standard connection they used to do in those steel bridges past in time. You can see that they remove the top flange of the beam, and then they weld an end plate to the web of the beam, and then they bolt that end plate to the main girders of the beams. So that connection, which is very common, is prone to have a fatigue failure. You can see on the right picture the crack that develops in the connection between the top flange and the web of the beam, and that's produced by secondary restraining forces that were not taken account during the original design of those steel bridges. Some of those bridges are older than 50 and even 100 years old, and they're getting to the end of their life service, and they need for repair. In Acciona, we developed a technology that's consisting of a carbon fiber plate that is bonded to those steel beams through an epoxy adhesive. We make a slot, and then we place a monitoring system on the carbon plate and also on the steel beams. Then we monitor that bridge you saw in the previous picture for more than 1 year. And then we measure the accumulated strain on the steel beams that were reinforced, the ones that were not reinforced, and also on the carbon plates. we found that the steel beams that were reinforced with the technology shown less accumulated strain fatigue, and also the carbon plate show even less fatigue than the steel beams. So the results were successful. We were be able to prove that the accumulate fatigue on those beams is smaller, and also we were able to reinforce a very difficult geometries with a very high adaptability on the carbon fiber. And future works in Acciona, we will keep researching on the bond connection between the carbon plates and the steel. We will check also the frequent vibrations that suffer that connection during a long period of time, and also we will check different environments and aggressive environments to see if the connection still works after 10, 20 years of surface life. We also have a second demonstrator in Finland to improve the shear capacity of railway bridges. The idea was to create a technology that was going to be able to reinforce the shear capacity of through bridges, reinforced concrete through bridges. That it was a very common type of concrete bridges built in some of the European countries in 1950s till 1990s. The problem with those bridges is that the inside of the bridge is covered with ballast, so you don't have access to all of the faces of the concrete bridge. And then we developed one technology that consists in a carbon rod that inserted within the lateral beams and bonded using epoxy adhesive. We carry out the monitoring, the demonstrator, and we monitor for 42 hours, more than 20 trains passing over the bridge, and we were able to see the strain deformations on those bars. We proved that the reinforcement is able to absorb the shear loads on those bridges, and we also proved that the monitoring system we used, which was a fiber Bragg rating, was able to catch those small strains on those bars. Well, Acciona, we will continue with those reinforcement in concrete bridge. That's part of activities we usually carry out in our company. And we also will push, we will push in the standards, in the civil engineering standards to make more convenient for the concrete carbon fiber repair and reinforcement on existing civil engineering infrastructures. And that's all from my side.
Thank you.
Good morning. So the work that I'm presenting is a collaboration, or I have the collaboration of Malchaba and Tiago from the University of Minho. And so the main idea is to use the fiber reinforced concrete applied with the new technology of shotcreting. Because in general, for the rehabilitation of railway tunnels, we use grid mesh, and we apply in the surface of the tunnel almost the same material. And why? So if we have certain zones where with more damage, why not to use in this particular zone more advanced material in order to save at the end, to save costs, obviously, to save money and to have a more sustainable approach. So the idea is to develop a new paradigm of the use of fiber reinforced shotcrete concept for high performance strengthening interventions in underground construction, which is aligned with the goal 9 of the Union 2030. So this is an example. So you see in the top part of the slide in the left, different tensile properties of several types or two types of fiber reinforced concrete. What we designated strain softening fiber reinforced concrete, that when attained the cracking of the matrix, it enters in abrupt softening, while we can use different types of strain hardening fiber reinforced concrete, where after crack initiation, we have increase of load carrying capacity of the tensile. So, and consequently, so why not to use these two types of materials in, well, there's a lot of symbols, Chinese symbols, okay. So we have two, I'm using now in this case, the laser points. So we imagine that we have the dislocation of a block, and then this dislocation of a block in the tunnel, and imagine that we have also in this zone a weaker material, weaker soil. So in this case, what happened? We have this type of deformation. So this is the critical zone. So in this case, why not to apply the fiber reinforced shotcrete? So this is a Mansouri tunnel, and then we can use different types of fiber reinforced concrete. In this case, we apply in this critical zone a certain material, a certain fiber reinforced shotcrete with a, I should say, relatively or intermediate mechanical properties, while in the remaining part we have a strain softening fiber reinforced concrete. But in this case, in second solution, that is strength plan 2, this is strength plan 1, this is strength plan 2. So we only apply in the external phase a much better material. So we applied in the external phases. Why? Because in the external phases, we have the propagation of the cracks. So, and when we evaluated the load carrying capacity of the tunnel, so in these curves is the scenario 1, is the one where we don't have weak soil, so we have a regular soil in all the tunnel. And in scenario 2, this is dashed line. So is the response of the tunnel with weak soil. And then we applied, when we applied the strengthening intervention, so the strengthening intervention plan 1 that corresponds to this strengthening situation, where we use a relatively an intermediate toughness material, we were not able to recuperate the tensile capacity of the tunnel and even the stiffness. However, when we apply only in the two external layers a very high tensile strain hardening capacity material, we realize that we are able to recuperate, even to increase the load carrying capacity and to recuperate the stiffness. So when we compare this situation of this strengthening with the other two conventional situations where we have two outer grid, steel grid mesh, well, this is the case where we maintain the same thickness for the strengthening layer, and in this case we increase the thickness and we apply only one grid. In order, the idea is to have the same flexural capacity for these types of solutions. And when we compare, we realize that considering a square kilometer of a railway tunnel requiring strength intervention, an economy of 53 million euros and 84 million euros is obtained when adopting the strength plan 2, this is this one, over when we use only with a grid mesh, that is this case, or to a grid mesh, that is this case. Regarding CO2 emissions, a reduction of 22 kilotons is obtained when the fiber reinforced concrete, fiber reinforced shotcrete solution is adapted over the solution where we apply only one grid mesh. So for future, the idea is we want to apply in any point the material that is obtained from this design approach. So in fact, it is necessary to have a new robust shotcrete system that is in direct contact with the output of the software. And this output of from the software includes also information from a railway tunnel digital twin, includes the geometry as well as damage. And for damage, we also we intend to use artificial intelligence to cataloging the damage and to transform this information for design purpose. And that's it. Thank you very much.
Hello, good morning, everyone. So my name is Pedro Montenegro. I'm representing here the team from Porto, but it's important to say that this work is also a joint collaboration with KTH, okay? And I'll talk about bridge damping. So why we are working on bridge damping? As you can see here, these are results that we got from In2Track3 from some measurements made both in Portugal and Sweden. And you can see here when you compare the damping estimation, especially in these bridges with lower span, with small span bridges, we can see that a large scatter of damping here, and most of the results seems to be much higher than the damping proposed now from the Eurocode. So the objective here in In2Track3 is to revisit these results, try to understand, to estimate damping with more advanced techniques, but more important than that, to try to understand this scatter, and if it's possible to, from these results, try to improve the current damping criteria from the Eurocode. So here's some short summary of the results that we got. We revisit some of the bridges, mainly the simple supported bridges that we have in Portugal, in which the free vibration period from which we estimate damping is controlled by more than one mode. So you have here we cannot apply directly the typical logarithmic increment method. So we applied more advanced methods, so the Prodi method, and we got good results in terms of damping for both critical modes, and we also validate these with some numerical models, which gave us good results and good perspectives. But more important than that is what we see here. So in the lower graphic, we see a similar graphic as I mentioned before. We have a great scatter of damping results for these small span bridges. Here we are comparing the red dots are the results that we obtained from the experimental tests, and the black dots the results that the ARI D214 committee obtained 20 years ago. And you can see that there is some coherence in the results. So this scatter also appeared 20 years ago. What they did 20 years ago, the typical and normal thing that I would do as well in that time. So we use a lower bound of the damping, conservative value, and this is the values that we have now in the Eurocode. But when you look for some of the small span bridges that we saw in Portugal, we try to understand which parameters most influence this scatter. And you can see here that as the acceleration amplitude that you use in free vibration period increases, we can see that scatter starts to reduce substantially. And this is very exciting result, because damping is particularly important under resonance, where we have large values of acceleration, and you can see here for larger values of acceleration. So each dot here is a damping estimation for the same bridge, but with different train passages, okay? And you can see here that for larger values of acceleration, we have a much lower scatter. So we are trying to see if it's possible to propose some recommendations for the future for these specific criteria, because this criteria is very important. It's very important when you design bridge, because it conditions the bridge design a lot. So what you do next? Now we start on September a new European project funded by the Eurail as well, in Bridge for You. It's a project where we have 11 partners. 2 of them are partners that already work in this project, so Porto and KTH. But the objective of this project, try to propose new recommendations for different criteria, and one of them is this damping criteria that I just talked. So we expect good results and good perspective and recommendations in the next 3 years. And if you want to visit the website and follow us on LinkedIn, we hope that we have good results in the next 3 years. So continue to follow us, because it will be the continuation of our work here in In2Track3. So thank you very much for your attention.
Good morning. My name is Jens Nilsson, and I'm presenting. I'm presenting this work on behalf of my PhD student Qurosh Nasrullahi. In transition zones between two different track forms, there is a discontinuity in track structure, leading to a stiffness in gradient, a gradient in track stiffness. And examples include transitions between two superstructures, for example, slab track to ballasted track, or between two substructures, for example, embankment to a tunnel or a bridge. So the differences in loading and support conditions at the interfaces between the superstructure and substructure on either side of transition may lead to differential settlement soon after construction and an irregularity in longitudinal level. And here you see one example of a transition zone built at Gransjö on Malmbanan between the 3B slab track and the ballasted track. So when we get this differential settlement, this leads to an irregularity in longitudinal level, and this increases the dynamic loads on the track structure. And thus there is a transition zones are prone to deteriorate at an accelerating rate. Simulation models, there are many in the literature on track settlement. Many of them just account for maybe the axle load, the number of wheel set passages. Very few account for the variation and redistribution of loads to adjacent sleepers that occur over time due to this differential settlement. We also wanted to use this opportunity where we have this transition zone on Malmbanan to measure long-term measurements in a transition zone. So here is the model that we're using. It includes to the left a ballasted track, rail on rail fastening, sleepers and ballast, and to the right a model of the 3B slab track, where we have blocks and then a base slab. We use an iterative approach where we simulate the dynamic interaction between the vehicle and track in the short term, and then we calculate the loads between sleepers and ballast and use that as input to a settlement model. And then in the next iteration step, we update the track model to account for these settlements. We can also account for an initial misalignment that often takes place in transition zones where we have an early compaction of the ballast, and that leads to a misalignment in longitudinal level. And we saw using this model that really the contribution from the stiffness gradient is smaller than the influence of the misalignment in longitudinal level. Yeah, I'm not. Is it starting? Sorry. Never mind. There is an iron train passing that transition zone here, and we can see that there are very large displacements of the sleeper close to the transition. The setup that we use for monitoring of long-term differential settlement at Gransjö included 30 fiber brag grating sensors, including measurements of sleeper displacements relative to a fixed anchor on sleepers 3, 5, 8, and 11 from the transition. We also measured sleeper acceleration, rail bending strain. We compared the measurements of sleeper displacements versus total station measurements to verify our measurements. And we measured from the beginning, just after the transition zone was installed in September last year until May this year. So we have long-term measurements of settlement. We could also see that there is really a large variation in support conditions between the sleepers in the transition zone. Some of the anchors could only be drilled down to 0.5 meter, whereas others could be drilled down to 2 meters because there were big blocks, big rocks below the surface. So future work, This work will continue. We will extend the track model to account for interaction between the sleepers via the ground. In the current model, we're only considering interaction via the rail. We will use the measurements that we have from Gransjö to calibrate the model, and we will continue optimizing transition zones, aiming to control the stiffness gradient and reducing the loads on the foundation. I will continue with another project that we worked on, and in this case, I'm presenting on behalf of Emil Aggestam, who was a former PhD student, and he's now working at Trafikverket. So now we're looking at slab track structures. And slab track is a robust structure offering higher availability and requiring less maintenance. In particular, track geometry is often more stable in the slab track. However, major disadvantages are higher construction costs and environmental footprint because of the large amounts of steel and concrete that are being used. Also, noise is generally higher from slab track. So there is a standard, EN 16342, that defines how to design a slab track. But in this standard, the bound and unbound layers of the slab track are just simplified into uniform structure, resting on a Winkler foundation, and a static load case is applied with a dynamic magnification factor. It's really difficult to optimize the slab track based on this standard. So we are, in this project, we looked into different key requirements for a slab track design, including structural integrity and robustness, of course, but also considering life cycle cost and environmental footprint. So we have a model similar to the slab track, transition zone model. In this case, we're modeling a slab track. You see the rail with an irregularity on top. You see concrete panels, and you see a base slab. And below the base slab, there is a variation in support stiffness indicated by the differences in length of the springs. So this is something that we have used to look into various load cases that are not being considered in the standard. For example, accounting for different levels of track irregularities, weave flats leading to very high frequency excitation of the slab track, a foundation washout where parts of the substructure has been washed away by heavy rainfall, perhaps. The upper figure here illustrates the bending moment distribution leading to tensional stresses in the longitudinal direction because of a washout. The bottom figure illustrates the maximum principal stress that has been calculated for different panel thicknesses. And these are compared to the flexural strength of the concrete. We see here that, well, we have calculated also for 3 different bed moduli of the support. And we see that if the panel thickness is smaller than 10 centimeters, this will lead to fracture or fatigue of the slab, of the concrete panel. However, if we had used the standard 16342, the outcome would be 19 centimeters. So using this model, we can see that there is really a large potential in reducing the amounts of concrete and steel reinforcement that needs to be applied. Generally, as I just said, the standard leads to overly conservative designs, resulting in higher life cycle cost and environmental impact than necessary. So what we did was to apply this model. We also had a model of reinforced concrete to look at crack widths and see if there's a possibility to reduce the steel reinforcement. And we applied multi-objective optimization to minimize CO2 emission and LCC while we are considering requirements on strength and robustness in the standard. We have written several papers on this topic, and we are suggesting that the standard is updated, for example, by considering dynamic loads, instead of just the static loads that are being considered right now. And also that the design is optimized with respect to environmental footprint. And model is able to study different conflicts of interest between life cycle cost, life cycle assessment, and structural integrity and robustness in more detail. Thank you.
Just a regular pointer.
So hello everybody, I'm Christian Ebner-Mürzl from voestalpine Railway Systems, and I'm going to present you by today 2 topics more or less, and due to the reason, as we've all already heard, one of our main targets or main issues is the life cycle cost issue or the maintenance things and things like that. And by that, we from voestalpine side have had the opportunity to develop or even integrate new tramway crossing in the work package 4 in the Shift to Rail project. And this is why or where we've started. We've already started it in the literature, research and issues like that, due to the reason that in tramway crossings in urban cities, in huge cities, it is always the issue noise, vibration, and the maintaining thing. So by that, we have had to decide or think about new tramway crossing, or how we call it, the concentric movable crossing. How can we improve this? By that, on the left-hand side, you can see an existing design with the more or less jump of the wheel from the one side to the other hand side. And this is, as you all know, if you have been, and I think everyone has been in a huge city, you hear tak tak, and then if it's not working, you need maintenance things would increase the time you need from one shopping center to the other shopping center by 1 hour. I know for railway perspective, it is not that much, but for humans, it's a huge amount of time. And due to that, we have designed or thought about the innovative design, and it came out through that it is the concentric movable crossing. It was more or less designed by our daughter company in Germany, and by that it is a really working and good working crossing. It is designed, as you can see on the next slide, through a whole more or less drilling blade, what is movable. And by that, it were some steps that need to be done. The evaluation of the design. So first of all, getting up the whole set of ideas, evaluating them, then think about it, how we can realize this thing. And then afterwards, as all of you mostly know, and I'm speaking now by today is from the supplier side, we've got a huge amount of universities here. We've got a huge amount of track operators here, but we from the supplier side, we have to deliver those things. And by that, you can't say, yeah, this is the idea. Buy it. We need to release the components, buy the components, design the components, release the components, and all kinds of stuff. And on the right-hand side, you can see what came out of this, and it is the concentric movable crossing. It is more or less, we've faced some issues with the installation, but no worries on that. voestalpine managed it. We've introduced it in our track in Germany, so it is already fulfilled the whole TRL level as we described it in the grant agreement, and by that, it is more or less working. And yeah, the future things or the future topics, what we will work on is the functional testing. So it is already introduced in the track. The full scale testing will be hopefully with any kind of customer, what we are looking for, but for sure we will get someone of those. And then testing the whole components, all kind of components, because we are not talking about the whole concentric movable crossing. We are also speaking about the whole elementary build up of it, because when you buy something, for example, a car like that, it should work, but all those subcomponents need to be pre-tested, need to be pre-assembled, and all those kinds of stuff. And we will focus on that we will launch it in the next few years up to the market and get it into the market. Good. So coming to the next presentation, the shift-to-rail demonstrator turnout. This is more or less a hard topic of mine. It is one of the hugest and most demonstrative objective from the Austrian side, participating in the whole shift-to-rail project. It is, as some of you have seen yesterday, the iceberg. It contains beginning by the paperwork, ending up in the whole demonstration in Vienna leasing. It contains a creative project team, which means a huge amount of expertise all over Europe, and especially concerned in Austria, containing into one project teams, really developing one demonstrator for the Austrian railway systems. And the main target behind of it was to expand lifetime, reduce the maintenance cycles, as I've tried to explain through several discussions. For sure, it is not that proven right now, but it should be more or less the next step in turnout systems. This is one point what voestalpine Railway Systems tried to express with this demonstrator, and all partners of us, for sure we have to thank the ÖPB system to get it into the track, the MCL, the WIF, the Chalmers University, the Getzner company, the Maber and Kirchdorfer company, to contain and express their mindsets in the whole project team. And by that we could, or we will stretch the life cycle and will stretch the maintenance cycles behind this whole turnout. And by that, even due to our positive mindset, we will skip some of the maintenance cycles what you already have to do in your track system. And by that, we can lower the downtimes, we can lower the maintenance costs, and even by that, we can stretch the whole life of this turnout. And by that, it is more or less the main target what we are facing through the whole project, is that the ballast destruction needs to be downsized and needs to be optimized. So coming now to the more or less called results of the project. By that, I'm also representing colleagues of mine. And on the right-hand side, you can see a more or less snapshot of it, how the turnout was installed in Sedgwick, in my hometown, or in where my company is. And so you can see what we have tried to optimize. We've tried to optimize the crossing system. It is more or less an optimized crossing system with tension, which is tension optimized, and sleeper discussing, and all other kinds of stuff. The enhanced bearer system, it is more or less, for sure, not the perfect bearer design, but it can optimize the whole life cycle. And yeah, it is working and it is proven, but for sure, due to the reason that the project, the Shift to Rail project, started in 2016 and ends up by this month, we will prove, or we have to prove from the supplier side on, and also from the operator side on, this turnout over the next years. So by that, we are facing to get it into the track up to many years right now, and then we can prove all those things presented by today. We've got some figures, we've got some measurements, as I've presented already through the last days, and yeah, but it is working. Then we've got the enhanced switch and crossing rails. Therefore, we've got the self-detecting switch design, which is more or less a thicker profile of the whole switch, and it minimizes one detection systems. So also one optimization of it. Then the bearer coupling system, for sure, it is cost expensive, but it works. It is on the backside of the turnout, and it smoothens the whole turnout and the load distribution above the whole system. And on the last points, those three ones are more or less our signaling parts, which was, or which were for our side, the first opportunity to conclude all kinds of our signaling system in one turnout. So by that, it also worked quite well. We've got data out of it. We can produce data, and by that we can analyze this data and evaluate the whole turnout itself. And on the right-hand side, you can see below some kinds of where we try to find solutions up to the whole project. And on the last one, I will introduce the Rail UHC400, which is also one more or less new point introduced by this turnout. It's a new rail grade. Good. Coming up now to the more or less call it assembly and the things what were introduced through the whole project. And by that, it is more or less, as I've tried to explain by yesterday, starting at the paper, and on the right-hand side, you can see the installed turnout in Vienna leasing. And by that, for sure, everyone wants to know how is it working. By that, we tried to more or less define some strategies, some, call it like measurement strategies to prove, evaluate, and compare these turnouts. And by that, we've got the possibility to install 2 demonstrator turnouts in Vienna leasing. And by this other hand side of this track, we've got 2 reference turnouts. And for this, we've decided to more or less go the way by 3 different measurement strategies, which is meaning on the one hand side, we are permanently measuring those systems 365 days a year. Doing measurement campaigns, what you can see on the left-hand side with the blue check rail blades, and do short time measurements, which you can see on the picture below. What we are doing to continuously monitor the system, continuously monitor the turnout and compare it with the reference turnouts to see how they perform. So, and for the future work, we will for sure work on those turnouts due to the reason, as I've tried to explain, 3 years of installing In2Track, because the turnouts have been installed in November 2020. Now it's 2023. It's for a railway turnout, not that long time. So we will manage to measure the things longer, continuously improve the whole measurement systems, talk with the customer, how is it working in track, what is good and also what is bad. Not only the good things, you know, from the bad things you learn, and talking to the customer, you know, on not even on the management level, also on the maintenance level, it is the real facts, what we can figure out of it. Compare the theoretical things, what we have developed by 2016, 17, 18 with the real hard In2Track by right now, and then evaluate and collect all those things and even try to integrate this into the new standards of the Austrian railway systems. Thank you.
Now I hope we have Tobias with us.
I'm here. Hello.
Hi, welcome. Please.
Okay. So I've talked before, I think an hour ago, about scale deposits in tunnel drainages. So please go to the next slide. So I think this is, hope this is clear. And what I pointed out before, that we have several projects to try to reduce the impact of the maintenance which is necessary for this on our train operation. And this here is that we want to construct a remote controlled flushing device, which has also a very low impact on our train operation, because nevertheless we have to remove the scale deposits by flushing. So next slide. So you see on the picture on the right hand side, you see the usual conventional drainage flushing, and as you can see, you have there a low floor wagon, and during this time there it isn't possible to have train operation. So next slide, please. So that's why we designed in the course of In2Track3 and in former projects of Horizon 2020, we designed this MDR flushing device. So MDR, it's an abbreviation for Modular Railway Drainage Flushing System. And so this is it's a flushing device, as you can see on the right-hand side in the upper picture, and it's transported by the MDR transport unit, seen in the lower picture. And this is transported by a kind of low floor wagon later. The flushing device itself, it consists of several modules like a high pressure pump, a high pressure hose, and a hose drum. You have robotics to place the nozzle for the drainage flushing in the flushing lines. We have a steerable high pressure nozzle with a HD camera and so on. And so this is a really demanding device. And the MDR transport module, it's demanding too from the point of planning and later from the point of construction. It consists of a container support frame, a container garage, and you need telescopic handlers to load and unload the MDR flushing device. So to the next slide, please, or to the last one. So this slide is also about a month old. So because we are really at the end of a EU-wide procurement procedure to get the contract with the company for the detail engineering of the MDR prototype, because what I showed you in the slide before, it was the tender design, which is the basis for the detail engineering when you have a company. This company should also not only engineer, make the planning, but also construct a prototype and test this prototype in the Granittal tunnel. This is a new railway tunnel in southern Austria. Partly this will be under scheduled railway traffic. After the testing, we will do a revision because we will see some aspects how they really work in reality. We will have a revision of the MDR flushing device and of the transport module based on these testing results. And after that, we will do regular flushing with this newly developed device. When we do this, we will get experience for the real long tunnels, because the Granittal tunnel is just 6 kilometers long. So in our terms, it's a short tunnel. And the Quorum tunnel or Semmering Base tunnel, they have a length of more than 25 kilometers. And there we really will need this device. And so we get experience for this. And because we will also need an EU-wide procurement procedure for the flushing of these tunnels, and then we will use the experience we now get. So I'm at the end of my presentation. Thanks for your attention.
Thank you very much. And now it's time for break again, and we will resume here around 12 for the next, well, right before 12 preferably, for the next presentation that will start at 12 o'clock. Thank you. So let's start the next here with predict behavior is our next session. How can we predict the deterioration of the railway so that we can plan and optimize maintenance and ensure that actions are taken before safety issues or traffic disruptions occur? And we have our first speaker. Welcome, Urs. Whoops, sorry. There we are.
Hi, I'd like to talk to you about our work to check which steel grade is suitable for which part of the network. The next slide shows the challenges we wanted to address. There are actually several different kinds of steel grades that a railway infrastructure manager can choose from when they want to build their track. There are a little bit softer rails and there are harder rails. And to see if we use the correct guidelines for placing these rails, we try to challenge the current guidelines that we had. Those guidelines we had were based on work by external organizations, for instance, by the UIC. So what did we do? We took all the ultrasonic defects that we had, so all the rails we had to replace, and checked on the common criteria they had or they didn't have. The results are on the next slide. In the top picture, you see the red dots are the slightly softer rails, and the blue dots are the quite hard rails. And the black lines are the current boundaries that we employ. And we here check the criteria of curve radius, that's the horizontal axis in the top graph in all of them. And we compared it to the load of trains, so the amount of trains that are traveling over these tracks daily. The little black lines in the diagrams are the current boundaries that we use. Unfortunately, we didn't see too much meaningful results here. So for the defects we characterize, the criteria we use to differentiate between the two steel grades were not very meaningful. So we just knew here that we did not use the correct criteria to make this differentiation. On the other hand, we saw a very clear result in the lower graph. Here we have the defects that we saw in tangent track, so in a very straight line. And here we saw that the blue box plots have a considerably lower lifespan than the red ones. So a little bit contradictory to a common belief, to a first intention, is that the softer rails, the red ones, have a significantly longer lifespan in tangent track than the blue ones, the harder ones. This has already been quite clear in the industry, but here we now have our proof with the data. These are about roughly 10,000 data points that make up these diagrams here. So that's the results we got. And on the next slide, we have also some future work. So in the course of our work, we realized that we might have a bias in our data. So when we decided to look only at the defective rails, then we didn't take into account if there are also rails that survived in the same application criteria and did not develop defects. It's a little bit like looking at all the people in hospital and then see that everyone is ill, and we need to take these data into perspective with all the rails that did not develop flaws, and that's what we will do in the next steps. So we will do a so-called survival analysis of the rail grades, different rail grades that we use under the different conditions, and we will see what we learn from there. Thank you very much.
Thank you, Urs.
So, ladies and gentlemen, my name is Johan Ahlström. I'm a professor at Chalmers University of Technology in Sweden. I'm here to present the work of a larger group of PhD students and senior researchers on anisotropy, thermal loads, and crack growth in rails. I have the names listed on the last slide instead of the first one, actually. Okay, what did we look at? We basically, like Urs just mentioned, the different rail qualities can have different effects on crack growth, etc. So we have focused on this little surface layer of the rails that is affected by the rolling contact forces, stresses, shear stresses. And on the picture here, you can see the accumulated deformation after a long time of operation. Also, there are 3 white lines that are put in just to illustrate the huge movement of material. And this creates an anisotropic microstructure. And as many of you know, we develop head checks and other defects in this very surface layer. So even if it's a very small part of the railway system, it's kind of important. So what we are doing, we are working with what Urs mentioned, the rolling contact fatigue. And we see the second graph coming in there. We also have a work hardening of this layer. Because of the plastic deformation, we get work hardening. Can that be beneficial? Yeah, probably. We decrease further plastic deformation. So when we grind, then we remove this work hardened layer. We want to remove the cracks for sure, but what effect does it have that we remove the work hardened layer? And what is the optimum say maintenance guideline? How much should we grind every time? How often? How frequently should we grind different lines and so on? So we have done some, I wouldn't say basic research, but some rather coming from the other way, not from the application, but from the research side, trying to understand the properties of this layer, how it develops in application like conditions. So it's of course impossible to take this surface layer of the rail and examine in some kind of mechanical testing facility, because it's a super thin layer, it's already cracked, and we have a gradient as well. So it's very difficult. So the results of one of the PhD projects has been working on what happens when we expose this layer to both increased temperature and mechanical straining. And the graph there shows a thermomechanical fatigue experiment that is actually done on wheel steel, because as you know, block braked wheels get up in temperature and down in temperature, and there are stresses involved. The second pictures there show a very advanced experiment at the European synchrotron facility, where we have measured the actual strains in individual grades. So why is that important? Yeah, actually, if we want to be able to predict stresses and strain and how they develop, if we want good predictability, we need those rather advanced experiments. This is perhaps a little bit more close to the application. It shows this method that we have developed in the previous In2Track2 projects, and now continuing to use and develop In2Track3. It shows this surface layer again, and then it shows 2 test bars that we have pushed and twist in order to simulate the same microstructure that we find in the surface of the rails. We can simulate by torsion and twisting. Then we can drill out a hole in these specimens to have only a constant shear deformation that represents a certain depth below the surface. And then we can make advanced experiments, multi-axial fatigue experiments, to understand the mechanical properties of this layer. We can also initiate cracks, and in this case we have used a notch to know where that crack will start, to easier be able to monitor crack growth from this. And we can see how cracks advanced depending on the previous shear deformation that we had. So it basically represents different depth. Okay, the last part is modeling of this. So for all these different types of mechanical tests we have tried to find ways to model. We've tried to find ways to model when will failure occur. So that's the work of a third or fourth PhD student, depending on how you see it. So it's, of course, way too complex to cover 3-4 students' work in one single presentation. So I gave just as an example. And we are happy to continue in Europe's rail
with those type of experiments. Just one picture here is we're using online monitoring of the rail top to find tracks. We try to have this kind of more applied, innovative ways of examining materials as well. Yes, you can see some names. Knut Andreas Meyer, Daniel Gren, Anders Ekberg has been involved. We have Dimitris Nikas, colleagues at DTU and ESRF, and also now Nasrin Talebi, Magnus Ek from the material modeling side. So that's a very brief overview of what we have done. Thank you.
Thank you.
Yes, so hello everyone. So I'm then Björn Pålsson from Chalmers and Charmek, and I'm going to talk about monitoring and prediction of SNC condition. And the work I will be presenting here are results from the PhD project of Marko Milosevic that has spanned on the In2Track2 and the In2Track3 project, and with supervision then from Chalmers and from Trafikverket. So the challenge addressed. So the main research question we have had in this project is whether we can identify the crossing geometry irregularity, impact loads, and ballast properties from measured sleeper accelerations. And why is that of value? Well, naturally, SNCs are known as hungry assets with high deterioration rates. And if we have, for example, a cracked crossing, that can lead to large downtimes and traffic disturbances, etc. So to know the condition of our crossing panels is of importance. So what we are investigating then, if you look at the photo there, if you have an accelerometer just next to the crossing transition, and then you record an acceleration trace when a train is passing, as you see in the plot there, can we then identify these quantities? So ballast stiffness, I think, is quite straightforward. Also the wheel rail contact force, that's also quite straightforward. What I mean by the crossing irregularity is this vertical wheel trajectory that the wheel experiences as it rolls over the crossing transition. So it's the relative vertical wheel and rail displacement. So the vertical excitation, simply. And we would claim that we can do that quite well. And how have we done that then? So it's a methodology including a number of steps. So I will talk you through them one by one. So top left, yeah, we measure sleeper accelerations, as mentioned. Then the first step is to do a frequency domain integration. So this is essentially just a double integration of the acceleration signal to displacements. And then you say that that's very straightforward. You can do that in elementary school almost. But in practice, it's not so easy with all the disturbances, etc. in track. So what Marko has done is investigated many different methods and came up then with a method that involves frequency domain filtering and integration to do this robustly for many different SNCs. So when we know the track displacement, we can calibrate our simulation model there. So we have a multi-body simulation model of the train, or a bogie in this case, and a finite element model of the track structure. So we can calibrate the ballast stiffness of this model to accurately represent the ballast conditions at the given SNC. We have to assume that the rest of the superstructure sort of has nominal properties, but they are also much more known than the ballast conditions, right? But by doing that, then we can calibrate and know the ballast stiffness at the given location. So then we know the system properties, or we know the properties of our crossing panel. Then we move on to inverse load identification. So what we do then, we solve an inverse problem. We know the input signal at the sensor, and from that we identify the wheel rail contact force at the crossing transition. And then you say that that is not possible. You have 4 wheel rail contact loads and only 1 sensor. And then I say that that's correct. So what we assume is that the loads on the other 3 wheels, they are constant. So we are able to identify the train type. And then we just identified the force at the crossing transition. Yes, but knowing then the forces, or at least thinking we know them, we can apply those to the wheel and to the rail, and we can compute the displacements. We can then subtract the difference, and then we have identified this track irregularity. It comes with some caveats. So, I mean, you have a single sensor in track. It's quite nearsighted. You can only really see what's happening ±2 sleeper spans away. So there are some limitations in terms of the frequency range we can observe here. So, and also as we are measuring accelerations on the sleeper, a lot of the rail or the high frequency rail vibrations, for example, are filtered away by the pad. So we can't go too high up in frequency. And also the crossing irregularity, we can't identify sort of the full shape. It's only the more high frequency content. Yep. But future work on this topic then. So yeah, industry actors have shown interest in these results, but it's of course always difficult to know what's actually being implemented in a commercial solution. These results will be taken further in a coming PhD project. It's called Digital Twin for Improved Maintenance of SNC. Yeah, so there the question will be how to use this condition monitoring scheme to optimize maintenance for reduced LCC costs. More information about this work can be found in the deliverables from In2Track3 and in journal publications that cover the work both from In2Track2 and 3. Yeah, so that was all from me. Thank you.
Thank you. Now we have Gerald with us, I hope.
Yes, thank you.
Welcome.
Hello, I'm Gerald Trummer, and I'm working at the Virtual Vehicle Research Center GmbH in Graz in Austria. And I'd like to present you today the research activities that we have carried out on modeling rolling contact fatigue with a focus on the consideration of the influence of the material microstructure and plastic deformation. Next slide, please. As we have heard before, the wheel-rail contact frequently causes a severe plastic deformation near the surfaces of wheels and rails. And in this layer, microscopic cracks grow that you can usually observe as the phenomenon of wear and or rolling contact fatigue on a macroscopic scale. And I'd like to present you today two models that address the modeling of this mechanism. We developed a so-called mesoscale model and macroscale model. These models are embedded in a bigger framework, in a so-called whole system modeling framework, in which we combine different submodels depending on the specific needs of the investigation. Here we combine the mesoscale model that covers the material aspects of the fatigue crack growth or the RCF crack growth. We combine it with a macroscale model that covers the crack growth due to rolling contact and accepts input from multi-body simulations of railway vehicles. And this is all done to predict the fatigue crack growth under operational loading conditions. Next slide, please. Yeah, the first model is the mesoscale crack growth model, which is a DM-based model that is actually representing the material microstructure. So we have explicitly pearlite colonies in the mesh and a submesh that's representing the cementite orientation in the pearlite. And the key task of this model is actually the prediction of crack growth rates as a function of the material microstructure and the plastic shear deformation. On the right side, you see two examples of meshes. The upper image shows you an undeformed microstructure with an initial crack in black on the left side, and then the red crack has been growing through this microstructure in a zigzag way. On the bottom, you see the same mesh, but now shear deformed to some degree. And what you can observe is there is an alignment of the interfaces of the cementite lamella, and the red crack that propagates through these microstructures, of course, does so in following the weak paths. Those are paths that are parallel to the shear plane. In the center, you see a diagram that's showing you the crack growth rate as a function of the stress intensity factor. And here a comparison is shown between what the effect of the change of the geometric crack path is on the fatigue crack growth rate. So the red dots relates to the undeformed microstructure, whereas the green dots shows you an higher crack growth rate that is observed in a simulation when you grow a crack under the same conditions through a shear deformed microstructure with this alignment. Next slide, please. The second model I'd like to show you today is the macro scale RCF model. This is one element of the whole system modeling toolchain that I mentioned before. It accepts as input the fatigue crack growth data of the mesoscale model from the previous slide, plus contact patch data from multi-body simulations of railway vehicles. It is a two-dimensional discrete spring network model that we combined with a local fatigue model based on bond strains. And the main objective is to simulate or predict crack growth or crack growth rates under rolling contact loading in a computationally efficient way. In the two bottom images, are showing you the mesh of a simulation or the simulation results. In black, we have an initial crack, and the thick gray lines are bonds in the model that have been broken due to the contact loading, and those represent more or less the cracked area. If we compare those results with actual experiments from a full-scale test rig experiment, then we see that this crack pattern actually is matching. The experimentally observed crack pattern is matching the simulated pattern. Next slide, please. Future work. We will continue with further refinement of the modeling toolchain and the submodels that we developed, hopefully together with industrial partners. If you are interested in reading more further details about those models, please have a look at the In2Track3 Final Report, deliverable D3.4. At this point, I'd also like to acknowledge my colleagues at Virtual Vehicle Research GmbH, who did the model development and the work. Those are Hamed Dawoudi Yonegani and Markus Januszewski. And if you'd like to know more about our company, please follow the links at the bottom of the slide. Thank you very much for your attention.
Thank you, Gerald. For the final presentation before lunch break now, we have Moncef on transition zone design and integration.
Thank you, Pernilla. Hello, everyone. My name is Moncef Toumi from Raynium, and I'm presenting today the work on transition zone design and integration, which is the result of a collaboration between the University of Huddersfield, the University of Gustav Eiffel, and Raynium. Next slide, please. So first, what is a transition zone? Transition zones are generally defined as an area in track that are subject to substantial differential settlement due to abrupt changes in track construction leading usually to support stiffness variation, increased dynamic loading, and stress variation in support layer. Different type of transition zones have been investigated within the In2Track3 project. You may saw during the previous session the presentation from Jens Nielsen about the transition zone from slab track to ballasted track, for example. And in this task, we have been focusing specifically on a special case of transition zone, which is the switches and crossing, and where significant change in the superstructure properties occur. These changes include variable rail pad stiffness along the switch and crossing, variable under sleeper pad stiffness, sleeper masses, lengths, and several other factors. Also, when settlement in switcher crossing occurs, it typically results in voids forming under the sleepers, which further accelerate damage and fatigue of switcher crossing components. Therefore, it is very important to have a deep understanding of the impact of the superstructure stiffness, both on short and long-term behavior of the switch and crossing. And to acquire this comprehension, it is essential to develop tools capable of providing size prediction of the dynamic behavior and the differential settlement in order to be able to estimate the remaining asset life and also to plan and optimize maintenance. The next slide, please. So several numerical modeling solutions have been developed in this task. The presentation is just a snapshot of the work, so I will not go into the details of the methodology, but for more details about the approach, please check the deliverable D2.4 of the In2Track3 project. The numerical solutions that have been developed are able to model accurately the dynamic behavior of the vehicle-track interaction in switch and crossing and the transition to plane line. The main approach here is based on multi-body simulation, but we also use the co-simulation approach between a finite element track model for the switch and crossing and the multi-body system model for the vehicle. The numerical models are also able to capture the variable track characteristic in switch and crossing, including varying superstructure and substructure characteristic. And finally, one major numerical tool developed in this project is the iterative procedure capable of estimating the settlement in switch and crossing, taking into account dynamic and asymmetrical loading, including voiding. Of course, asymmetrical here means taking into account the fact that settlement at the right isn't necessarily the same at the left rail due to asymmetrical loading, especially in switch and crossing. So the dynamic model was calibrated and validated using measurement from the shift-to-way switch and crossing demonstrator already presented by Christian Ebner during the previous session. The calibration was used to determine the missing parameter like the ballast stiffness. You have at the right top a comparison between the numerical result and measurement of the steel harrow sleeper displacement at the right and the left rail. And as you can see, a very good agreement was achieved. Unfortunately, we didn't have available measurement of the settlement to validate the long-term approach. Therefore, a comparative study between a standard UK switch and the shift-to-way demonstrator switch was carried out. And you have at the bottom right the result of this comparison, which represents the settlement evolution along the switch panel at the right and the left rail for both cases. The next slide, please. So for the future work, we think that the methodology and tool developed this project to estimate settlement require further validation for or from an instrumented site or dedicated laboratory experiment. Further improvement should consider flexible sleepers in the vehicle-track interaction model, which should give a better accuracy, especially in the crossing panel where barriers become quite long. The level of discretization along a sleeper should be investigated as well, and specifically its effect on the distribution of differential settlement and voids. And finally, as I already said before, more information can be found in the final deliverable D2.4, section 5.4. And if you are interested, of course, in having more information about this work. Thank you very much for your attention.
Thank you very much, Moncef. And now we have a longer break until 1:30 for us here. Look, in Stockholm, it means lunch, probably for you who are joining on Teams as well. We will be back. I would like you in the room just to stay for 1 more minute. Thank you, and see you again soon. All right, it's 1:30. Let's get started. We go into session number 4 now, mitigation. So what if something has happened? What do we do then? If something's happened to the infrastructure, what can we do? And our first speaker here today, this afternoon, I'm sorry, is Phil Winship. Welcome.
Thank you. Afternoon, everybody. My name is Phil Winship, I'm Principal Engineer from Network Rail, and I've got the next 2 presentations. So this one, obviously, as it says, autonomous inspection. This is more a video of what we've done, so I'm not going to talk about everything. I'll just let the video speak for itself. But basically, with the autonomous inspection, we looked at using S&C drone inspection methods. So not using a drone that's just actually taking a video of the S&C and somebody watching it on a live feed on a laptop or something, which has been done in Network Rail before, and maybe other people have looked at it. This is looking at a slightly different view of how we actually can inspect S&C. So I'll leave the talking to the video. We're here at Wiston Junction, just south of Leicester. We're doing some flights with the drone to look at inspecting switching crossings in a novel way. The drone flies over the S&C, it takes still shots, and then the software that is being developed by Brown and Craven is then used to actually knit those images together to provide an orthographic image, which is 2D, and a point cloud image of the actual S&C. The images are really large. Each image could be hundreds of megabytes in size, and we would get sub-millimeter pixels on the image, and that allows us to spot even hairline cracks within the rail.
We're looking at detail that no normal human could ever spot in their walkthrough inspections. Network Rail supporting a project like this is phenomenal for all of us because it enables us to dedicate time and resource to testing and developing and enhance our ability to capture high resolution and consistent data sets. Because of the increase in quantity of data that we're able to bring back to our servers, back to our offices, we've built a system around machine learning, AI, to do that task for us. So we're playing a giant game to spot the difference between data collection rounds. So we've been here every 2 weeks, and our computer systems are now working very quickly at spotting any critical issues with that rail so that it can be rectified.
The footage itself is going to be enabling us to take measurements where we look at track gauge, for example, and also look at images to actually compare one inspection with another. If you zoom into the image, you can pan around the picture as you would normally navigate a map. And what you can see is on the left-hand side is the first visit, the right-hand side is the second visit, and there's a slider in the middle. The slider shows you the differences between the 2 images that were captured on different dates. And if I zoom into where I've added a flag, you can actually see that the clip has moved. If I turn off the image recognition, you can clearly see that the clip has actually been changed.
we can use photogrammetry techniques to convert the images into a point cloud. This then allows us to model the data into 3D models. And this is effectively a 3D viewer of the point cloud that we've collected. So you can see my camera position is in the view, and I can navigate around the scene. This allows the user to do various things, but the main points would be to measure distances, take coordinates of locations, but perhaps the most significant use case for it is if I zoom out, I can actually activate the UAV images that were actually taken on site. But what this allows us to do, if I remove our measurement tools, is we can hover over the image and it will project the image boundary onto the ground. So in this location here, say I wanted to read this label that's on this box, I can come back up to the images and say, well, that image there holds the information for that box. So if I click on the image, it will put me in a viewer where I can then zoom into the image and read that label within the box. Our main focus is to collect data efficiently, and we can fly the drones whilst the trains are running without risking safety of staff.
Keeping boots off ballast, as we say in Never-Rail, to actually move away from having people physically inspecting the track. So that's just a snapshot of where we are with that. We're going to take it further within Never-Rail, adding more artificial intelligence and machine learning in there to make sure we can actually start looking at more componentry level inspections. So we've got basic visual inspections we have where people are inspecting the track maybe on a weekly basis to have a look at what that looks like. Supervised inspection, which obviously look a little bit more in depth in terms of what the inspection means and what they're looking at in terms of dimensional checks, etc. So there's quite a lot more work we're looking at to add more machine learning into that. So we've got a system in track called PLPR in Never-Rail. It's like plane line recognition. So we're trying to do similar things using the drone technology and the footage to look at the machine learning capabilities of doing very similar things with drone technology for this particular aspect of taking people away from inspecting S&C the way we do at the moment. Because clearly at the moment, access is very bad for a Never-Rail, probably not dissimilar to any other infrastructure manager. And our access is mainly on a night. So inspecting on a night in darkness clearly has its drawbacks where we can actually augment that by using this type of technology. That's where we've got to with that one. So thank you. Moving swiftly on, we've got me again, unfortunately. Discrete defect repair. We've been developing this for quite a while. It's a system for actually doing automated weld repair of plain line rails. So this has been developed through the In2Track2, In2Track3 projects. It was something that was in its infancy out of the In2Track projects, but clearly we've moved it forward to now a very high TRL stage. So at the end of the project, Never-Rail are looking to take this forward and get product acceptance for it within Never-Rail to allow us to use it as a tool on track. And there's quite a keenness in the actual industry within Never-Rail to take this forward to actually move away from having a manual method of doing these repairs. So I'll just go through these slides. So ultimately, we're not unique in having rail breaks and rail defects. You've seen a few presentations earlier today talking about how we can actually manage those better and do more actual systems of using the data to actually look at where we can actually prevent maybe defects occurring, etc. But we're clearly going to still have to repair these. As you can see there, we have quite a high number in that sense in terms of how we can do that. This repair method is looking at trying to intervene at a very earlier stage. So instead of looking at something that is quite a deep crack in terms of a squat or something like that, we're looking at a depth of around about 10 millimeters as maximum. So this is trying to pull it back to the stage of removing all the downstream effort and inspections and possibility of having to change a rail because it's got too far, to taking that defect out at an early stage, reducing that downstream cost. I won't go through how we actually approach that. That's just obviously what I've said already. So this is some of the tasks that have been done. That's the DDR machine itself. Looks like theoretically a truck cab that's just been taken off the top of a truck and dumped on top of that. But it's just the way it looks. But it's effectively a fully automated system enclosed in that guarding, and you have a tablet with a system that shows you exactly the parameters of how that works, what type of weld parameters it's using. So we have an audit trail of the record of how the actual weld's been deposited, and we've got the record of that so we can actually take it away and obviously use that if we have to in terms of doing the investigations if there's issues in that. But this gives us a much more consistent method of actually repairing things, so it's not down to the actual skill set of the welder that's doing the job, and moving away from having people on track doing that work. Clearly, there's lots of health and safety issues with doing welding, not just about people being on track, the heat and all that type of thing, the fumes. This is a self-contained unit that does all of that for us. So ultimately, that's where we are at the moment. We're doing some, I think it's next month, as in tomorrow, December, we're going to start doing some trials, and that's going to give us a big group of evidence of actually using it on an infrastructure area. So I'll quickly move to this video. Hopefully I can get this working. I'll explain it a lot more than me.
Behind me is the J-Rod discrete defect repair machine. It is a fully automated machine for the repair of discrete defects on plane 9 rail. The clamps are going to go into position now, secure it, after which we will start the milling operation.
So I'm here today for the initial trial of the DDR units, with the next step being we're going to trial it on the southern region.
It's been developed to replace a manual process that is dependent on highly skilled operators, and even with those we have a degree of variability that can influence the long-term performance of the repairs. So we're looking for something that can give a much higher consistency and longer-term performance. The welding is taking place now. The welding gun traverses across the width of the rail head and does a number of traverses to cover the cavity that has been cut out. Each weld is done in sequence and then cleaned and cleaned. The loose scale that you're seeing on top of the weld will be removed by cleaning across the rail head.
The main benefit I can see of the DDR machine to both groups and regions is the lowering of maintenance costs, getting boots of ballast, aligning with modernising maintenance, and also providing an effective and efficient and reliable service to our passengers and customers.
This project is a fantastic example of the collaboration that the Shift Rail programme was able to offer, working not only in the UK rail industry but also with our European partners on their rail networks.
So this is an excellent example of both the routes and the central business team working together to give a real benefit to the bigger business and our customers.
As a project management graduate, it's great to be part of really exciting projects that I know will deliver real change to the railway.
It will deliver a far more cost-effective system for the repair of defects and provide benefits for the railways as well as the passenger community.
There you go. Thank you.
Thank you, Phil.
Hello again, I'm Andrew Brown, Principal Engineer, Network Rail. I want to talk to you about new scheme and material we're going to be using for the replacement of damaged tunnel lining. So the replacing of damaged or degraded tunnel lining is a difficult task. In the UK, we have over 5.5 million square meters of brickwork lining. Quality of these linings in these historic tunnels, where the average age is circa 150 years old, is on a downward trajectory, and current repair methods for small areas are unsustainable. So it takes currently 2 to 3 shifts, shift being about 8 hours long, to complete just 1 square meter of repair. Working at height is also required, as you can see. Obviously carries risks. Also finding bricklayers with the right skill set is becoming increasingly difficult. Access to undertake these repairs is hard to find, as I'm sure you can appreciate, and increasingly less time is available on the network to undertake repairs the way that we're doing it now. So new methods of undertaking these repairs require large amounts of access and removes the risk from undertaking this type of work is therefore necessary. So I've been working with the University of Loughborough. We've considered many different options for materials and the temporary works design, including 3D printed parts, but this proved financially prohibitive. We down selected to a material that can be pumped into areas of the tunnel lining where brickwork repairs are normally undertaken. The material has been extensively tested in laboratory environment, where it was needed to be proved the material will be sympathetic to the sounding substrate, for example, not creating any hard spots within the arch and allowing the arch to return to its full structural capability. It can be seen on the left that during a crushing test, the material, which is a 2-part resin, stayed intact and acted just like the surrounding brickwork and remained fully bonded. For the temporary supports, a flexible plate has been designed, you can see in the middle picture, and it's operated by hydraulics. We can move every individual strut, and that allows it to fit the profile of the arch perfectly. This is moved into position by a road rail vehicle. You can just see the yellow boom connected to the flexible plate, and once in position, the resin is pumped into the void. Flexible plates can be removed once the resin is cured enough, and this can take only 15 minutes, which is obviously a huge improvement on the 2 days it currently takes. So using this technique, we can repair multiple areas of the tunnel in one night, obviously removing the need for access-hungry repairs and resources which are hard to find. So future work. Well, we need to consider the design life. We're pretty confident we can get a good design life out of it for the test we've already taken. But that needs to be made official. Currently, the material is actually going through a freeze-thaw exercise on a 100-day cycle in the university labs. Something else we want to deal with going forward is the area still needs to be prepared by hand. So it still does need people to be working at heights, but obviously for not the amount of time we have previously. We want to make that an automated operation. The tunnels themselves were actually designed to allow seepage through the tunnel, as the Victorian engineers at the time couldn't deal with the hydrostatic pressures that they had to deal with. And currently, the resin we've designed is non-porous, so drainage needs to be designed into that material. We also want the material to be pumped into areas where ring separation, and that's the little diagram on the top right, which is an example of ring separation, has occurred. We have lots of areas of this within our tunnels. I think we're up to something like about 300,000 square meters of that. And the image on the bottom right shows that it is possible. Again, with the issue with the lack of porosity, we need to resolve that issue too. So we'll be continuing to undertake the research to full implementation on the UK network. That's it. Thank you.
Thank you very much.
So, good afternoon. I hope you had all a good lunch break. Yeah. I will talk today, of course, about tamping, because this is our main topic, and also one of my favorite topics. But before we do that, we have to talk about what is tamping, yeah, so that we understand, okay, why do we need tamping? We have a settlement of the track, and we want to bring the track back in the desired position. Therefore, we have to lift the track in the desired position, and then we have to penetrate with the tamping tools into the ballast and push the ballast beneath the sleeper to create a new foundation for the railway track. So now we know what tamping is. Of course, it's a little bit more complex than this, because if you are working with a tamping machine, if you are an operator, you have to take a lot of parameters into account to achieve a good tamping result, and in the end, a long-lasting track geometry. You have to decide about the correct tamping force. What you don't have to decide, because it is given by the machine, is the frequency and the amplitude of the tamping tools for compacting the ballast. But what you have to decide is the correcting values for the lifting and lining. Maybe it's given by the infrastructure manager. Maybe you have to do a pre-measurement run with the machine. You have to decide about the tamping depth. So you need to know what kind of superstructure you have at the current situation. So what is the height of the rail? What is the height of the sleeper? And then you have to decide about the squeezing time. And then there's one point missing on this slide. What you also have to take into account is the ballast condition. So you need to know what kind of ballast do I tamp with this machine today, and how do I have to choose the right parameters to achieve the best compaction result possible with this current situation. And if you think about automatization, then in the end, in the future, when the machine will be a robot, the machine has to also take into account the ballast condition and all these parameters to decide which combination do I choose to achieve the best compaction result. And this is what we did, not only in this project, also in other projects, but in this project, we worked on this topic. Therefore, we equipped our tamping machine with several sensors that we can measure what happens during the tamping process with the ballast and also with our tamping machine, with our tamping tools. On the right-hand side or the left-hand side for your perspective, you can see the machine that we equipped with all these sensors. This is a special machine because it's a hybrid machine. I will hurry up. It's a hybrid machine, so this could work also with the power from the catenary. And what is also special is we have equipped this machine with a system that can measure the absolute track geometry in combination with an inertial measurement system and a stereo camera system. We have some markers that you place on the poles, and these markers can be recognized by the measurement system, and then you can measure the absolute track geometry. Coming to the work that we performed within Shift2Rail, within In2Track3, we brought this machine to Sweden. We homologated it for Sweden, and we performed 8 night shifts in Sweden. We measured with our machine the ballast condition in Sweden. We took also some ballast samples, some ballast excavation, compared our measurements with the measurements of the ballast excavations. And by combining this also with the measurement system, we knew exactly where we measured all the results. We learned a lot out of this research. We will further develop our system. Of course, we need the information still from the infrastructure manager, but what our machine records fits perfectly fine to the excavation and to the information of the infrastructure manager. And we will also hopefully work together in future with Trafikverket to implement the new measurement system for measuring the lines and bringing also the absolute track geometry to Sweden. Thank you very much for your attention.
Good afternoon, Alejandro Salanova from Plaza Toira, and I want to summarize the story of how we built our first prototype for the urban rail grinder that we developed within Shift2Rail framework, and it's called the Plaza Atmo. So it started in In2Track, where we made a study about the challenges for the infrastructure manager regarding the urban railways, and some challenges that they claim are the short operating breaks, the increasing of loads on the rails, the increase in passenger numbers, and the sound and vibrations. We also found in this study that the rolling noise is the main source of noise emissions for the urban network. And also the infrastructure managers claim that the biggest defects they find in the rails are the wear and the corrugation as the top one, and followed by squats, wheel burn, and shelling. Also, the most common measure infrastructure managers use to reduce the noise and vibrations is rail grinding. So in collaboration with Vinalinian, the infrastructure manager in Vienna, we made the proof of concept of a urban grinding machine in In2Track. After that, in In2Track 2, we follow with the construction and first test of the prototype of the Atmo. These tests were performed indoors and outdoors in Vinalinian. And for the last part in In2Track 3, we performed further tests and also noise and vibrations. So this machine, the Atmo, was designed to fulfill the requirements that previously mentioned and the challenge of the urban railways. The Atmo comes with great flexibility. It can drive in curves up to 16.5 meters radius. It's also compact. It measures, it's 8 meters long, followed by 1.8 meters high and 2.1 meters wide. And it's automatic. We can control the Atmo by a remote device. It also comes with 2 different modes of grinding. Comes with a sliding stone. Basically, the stones are driven at the same time as the machine, or the oscillating stone, whereas the aggregates oscillate in longitudinal direction with the machine. Some results I can show here are the removal of corrugation. That is the main criteria we evaluated for the improvement of the corrugation on the railways. And here's a chart comparing both modes, the oscillating and sliding, after 10 grinding passes. We can see that we remove up to 90% of the corrugation with these passes. And lastly, we performed last summer some measurements regarding noise and vibrations. We measured the acoustic rail roughness with significant changes in emissions up to 15 decibels. The sound emissions, which could be reduced in up to 8 decibels in the Flex City, which is the heaviest tram used in Vienna, and the ULF and EXCX up to 4 decibels. And lastly, in vibrations, we found a significance of up to 50% reduction. And the future work on the topic, we have seen that the prototype of the Atmo has proved to be a machine which fulfills the demands of the maintenance regime for the urban railways, contributing to the removal of corrugation on the surface of the rails, and therefore also in noise and vibration emissions. Our next steps are the product development of the Atmo. We are working on different possibilities for the electrification of the machine. And we also offer this machine as a service. If you want to see more information about this project or any other research and development project from Plaza Toira, you can find it in the website in the research section. Thank you very much.
And now we have Thibault with us from Millennium. Please.
Yeah. Good afternoon, Thibault Lesage from Millennium. And today I'm going to talk about rail repair by a process called cold spray. So you can go next slide, please. A few words, as you said earlier, it's quite common actually to replace a rail when you got some defects. So we have a first step, which is rail cuttings and welding. And obviously, this process is quite expensive and time consuming. And we got some heat affected zone problematics. And if we look at the figure on the left-hand side, when we got some discrete defects, we don't have much solutions to repair them properly. So the goal of this project is to propose an alternative for rail repair. Next, please. And we choose to select the cold spray process, which is quite used in the aeronautics industry, but not so much not at all actually, in railways. Next, please. And a few words about the cold spray process in itself. So we use nitrogen or hydrogen gases, which is heated up to 400 to 800 degrees. Then we use a powder filter that has been fitted into a supersonic nozzle. Then we got some supersonic speed particle stream, which crash on the surface and creates the deposits. Next, please. And the main advantages of this strategy is we use very low temperatures, so we got no heat affected zone or very low energy consumption. We got a very fast repair with thick deposit available for more than 1 centimeters. And I think you can go to all of them, all of the different steps. So we start with the initial damage area. We remove it. Then we do the cold spray process in itself. We do some machining to get back to the initial shape. And finally, we do some not so optional heat treatment to get back to the initial material properties. Next, please. And as I said earlier, it's quite common in some type of materials to use cold spray, specifically ductile materials such as aluminum, but it has never been done on stiffer materials such as perlitic steels we use commonly in R260, for example, railways. So the first initial trial of spraying is indicated on this top side picture, when we can see very poor cohesion and no possibility of building up. So this first test was fully unsuitable for rail repair. Next, please. But at the end of the project, we worked a lot on the heat treatments and the spraying conditions, and we ended up with a powder microstructure and a final microstructure that were fully consistent with classical R260 steels, with the deposits of more than 1 millimeter thick and good overall properties. Next, please. So in conclusion, we started from scratch with barely any help from the literature, and we managed to have a several millimeter thick deposits with good adhesion and pretty much encouraging mechanical performances, which proves that rail repair by cold spray process is possible. Next, and we got some quite a lot of perspective actually, but the 3 main ones are an improvement of the spraying strategy, work on the technical feasibility of service rate to be tested, and finally the profitability to be tested. And last one, if you want more detail, you got here the deliverable where you can see all of it. So thanks for your attention.
Thank you very much. And you are not Nicolas, so please introduce yourself.
Hello, everybody. My name is Dorine Chenier. I replace Nicolas since he couldn't come here today. And I'm going to talk about joint welding of magnetic steel components. So about the challenge and the problems, we have several cracks of welding at the interface between rail ends and crossings that occurred for the past few years on the French railway, And the current welding process of SNCF Reza don't reach conformity to European norm weld standard. So in the picture, you can see example of weldings between crossings and rail ends. So the objectives of the project is, in one end, to develop an innovative welding process for rail ends by replacing standard rail steel, perlitic steel, by magnetic steel. And on the other hand, to ensure conformity to European norm weld standard of this welding process and to homologate it. And the main goal is, of course, to reduce the cracks at the interface between rail ends and crossings. in the picture, you can see the demonstrator. I will talk about it. So about achievements and the results. After lab testing and validation in In2Track3, a demonstrator on track was necessary. So a cast manganese crossing with magnetic steel rail ends has installed in south of France, in Narbonne, in March 2022. And it was monitored for 1 year, during 1 year. There were 4 visits, and during these 4 visits, the following tests have been performed on the weld. So we have measured vertical straightness on the running surface. We have measured hardness of the welds, and visual inspections have been made as well. About results, for vertical straightness, no collapse have been observed. You can see an example for one rail end, rail end B, in the chart. Regarding hardness, a little constant increase in all parts have been observed, which is acceptable and normal. And for the visual inspection, no crack or creep or rear have been observed. So you can see an example in the picture with a normal weld. So for the conclusion and the results are quite satisfying in 1 year of measurements. And we've got some positive feedback from crossing manufacturer, which is good. And about future work on the topic, even if we've got some positive result in 1 year, we know that welding cracks could appear after 15 years of use. So we have to perform some fatigue tests, other fatigue tests, and so next year fatigue tests will be carried out on 15 welds to assess the performance of these welds and to homologate it. And the first commercial order could arrive in 2025. So that's it. So if you can find some references here, and you can find some more information in the final deliverable. And if you have any question, you can contact my colleague at this email address. Thank you.
Thank you very much.
So I think it has become clear that welding is important but difficult. My name is Johan Ahlström. I am from the Chalmers University of Technology, and I'm presenting this topic on behalf of Björn Andersson, who is a PhD student with us. And we are actually 3 seniors helping with different aspects. Lennart Josefsson has been working with weld simulation his entire career. Magnus Ek is a specialist in material mechanics, and I work with mechanical properties of materials. So, rail repair, I mean, welding simulation is difficult in itself. For stainless steels, for manganese steels, and so on, it's difficult. But when we go to pearlitic or bainitic steels, we have another level of difficulty because those materials tend to harden with rapid heating and cooling. They tend to harden, form martensitic brittle structures. And we need, in modeling, we need to take all of these phase transformations that occur in the material into account. And we need to know the material properties at the different temperatures and before or after phase transformations and so on. So it's so much material data is needed for accurate welding simulation. And also very advanced simulation techniques are required. So both the material modeling part is challenging and the finite element simulation is required. We cannot use we can use a standard program where that there is a lot of programming required to handle phase transformations, etc. So these are some challenges, and here we can see some of the focus areas that we have been working on. If I move on to the results here, the first is just from literature to show how you can do rail repair welding. We have seen the DDR, we have seen other examples, cut away material that is cracked or damaged. And then we need to fill up this material volume and increasing the predictability of the properties and being able to test in the computer simulation environment, the preheating, the influence of climate conditions, etc. is really important. In the lower picture, you can see the attempts to, what can we say, to monitor and control the development of different microstructural phases, and also then to predict the residual stresses. But it's a challenging task. We are continuously feeding the simulation models with better and better material data. So the future work on this topic, the latest work of Björn has been to take the Swedish rail repair and simulate that one. We have examined a real repaired weld, and he's doing the corresponding simulation in the computer environment. And the next step there is to continue with the fatigue loading that occurs after welding. I mean, welding is one thing, but then we need to run trains on top of that repair weld as well. So that is what we are working on. Yes, I'm done.
Thank you. We have 5 minutes until the next presentation, so you can just take it cool. And we're going to stick to that timeline. So we wait 5 minutes and then we are back. All right, so we move on to the last session for this final event. Session number 5. That goes more on environmental topics and not what we think of plants and fruits and stuff necessarily, but more on the noise and vibration and surrounding environment in that sense. And we start with Phil Winship.
Okay. Looking at effective drainage management in this, obviously, I think the thing to just bear in mind in terms of climate change, as I was talking about the environmental aspects of things, network rail in the UK, not unique in terms of what's happening around the rest of the globe, Europe in particular, getting a heck of a lot more rain, especially this time of year. So how do we get rid of that rain and make sure we don't actually have some issues that disrupt the asset for rail travel? We have quite a lot of areas where we've had issues, we've had derailments, actually one, unfortunately, the fatality a few years ago, where a deluge of rain in Scotland caused a landslide, and it caused the train to actually derail. So there's obviously areas where we need to improve on trying to predict where these things might happen and what we can actually do to effectively look at the drainage management system. So this is what this project is really looking at. So obviously the problem there is clearly not unique to UK, as I said. So trying to have some sort of management system for drainage is obviously quite a very difficult thing to actually look at. You saw some presentations earlier about different ways of actually inspecting drainage, etc. This is more in looking at how the effectiveness of management of drainage actually can be implemented in a more machine learning way. So effectively the approach there obviously is looking at things from In2Track3, moving it further forward to look at improved machine learning for being able to actually look at algorithms that can help us estimate where that might happen. So this map on the right hand side looks at the probability of earthwork failure. So all those lines are the types of areas in different colours, looking at the more propensity of where we're going to get that sort of problems. This work is sort of linked to another project outside of the shift rail work within Network Rail, which has created a model for all our infrastructure, which looks at the catchment of water when it actually has a very serious downfall, not just about the actual track itself, it's looking at the surrounding areas to look at how much water might come off the surrounding farmers' fields, etc. And if you've got a cutting, for example, on the railway, that's more or less like a sump or a tank, if you want, where the water's going to start looking and trying to get to the lowest point. So this model that's outside of this piece of work is being fed in by some of the algorithms that have been developed here. So this is obviously an area for us to look at, not stopping it happening, because clearly that's not the actual objective here, but looking at trying to get some advanced notice of what's going on, how this might happen in terms of the actual volume of water we might see, depending on the actual rainfall, based between this 10 and 100 millimeters of rainfall within a 24-hour window. And he's trying to forecast maybe up to about 5 days ahead what's actually going on within the weather forecast as to where the rain may fall. So that's basically the work that's been going on there, and looking at how we can take this further forward, and looking at where we've got the better data assets. So it's looking to try and link to not only about drainage, but looking at track assets, other assets as well in other disciplines, to see what sort of condition are they in compared to whether there's actually a deluge of rainfall. So if you've got poor track formation, for example, your ballast is not in a very good condition, that's going to affect how that rainfall is going to impact that asset. If it's a brand new SSE or a brand new track layout, then the rainfall might not have the same impact. So it's trying to get that data then to actually improve that in future iterations of this work, to make sure that the model actually is more accurate in terms of specific assets, locations. One aspect that we've looked at the bottom there is looking at wet beds. So the consideration is whether is a wet bed the same wherever it is in the country, are there different characteristics of wet beds, and if we get a deluge of water, how much of that effect is going to have on that particular area where we've got a known site where wet beds have actually occurred. So that's another little bit of area where they want to actually extend this this research to try and actually how we can manage those wet bed locations much better. So that's just a quick snapshot of where we are with tracking drainage in a better way.
Thank you.
Okay. And you got me again. So this is just looking at moving clearly to a different area, but noise and vibration. So this is obviously something that is affecting everybody within the rail industry. We have presentations earlier about noise down to actually the roughness of the rail itself. This is looking a little bit more specific on slab track. So looking at vehicle noise on slab track is an issue, especially where we've got more slab track being introduced more as a general sort of better way of supporting the track. In England, we've got the Elizabeth line, which is just across London, which is totally slab track. So they've had to look at this in quite a serious area to look at what the implication of noise is in terms of how we actually can manage that. So clearly that's the area where we're trying to focus a bit more in this particular work. So it's really looking at the actual, in this case, what effectiveness of the pad itself has on that. So if you have a slab track, you really need a softer pad, because if you have a hard pad, the vibrations that are going through the actual, from the rail itself into the concrete that the actual slab is made of, that's not going to mitigate the actual sort of distribute the noise as easily if it was a hard pad. So we have to have a softer pad. There's these issues then as to going to the top of the rail with a wheel rail interface, how much of the effect of the roughness of that interface is causing noise or vibration, and how that filters through to the rest of the actual structure of the track itself. So that's basically how this is looking at, in a way of looking at doing a review of what actually the problem is, how it can be actually put on a particular area where we're looking for slab track vibrations here. Then looking at how to measure that. So they've been out doing a measurement campaign of that, looking at this particular demonstrator, and then comparing that with what ballasted track obviously is showing in terms of what vibration that demonstrates, to what a slab track looks like in terms of the same area but different structures, etc., what the vibrations might look like in that sense. And then obviously looking at how we can model that and how we can look at the noise that's actually radiated from that area to see what we can do to change that. So ultimately they've looked at different railhead treatments, so milling in this case, to look at how much of an acoustic roughness that leaves. Milling is an area we've started looking at a bit more deeply, but clearly there's an area where we need to look at what does that do from noise and vibrations point of view. So we've looked at that, and then clearly there's some areas where we're looking at what the wavelengths of the actual vibration that's created from that surface finish that the milling is given. It obviously helps in one sense, but not in another. So the long wave is controlled better, but it obviously then doesn't mitigate against the short wave. So we've got an issue there. We need a bit of a balance. But clearly from the work that's been done on the second bullet point there, doing some grinding and polishing after the milling's been carried out will help a lot. But obviously then that's doubling up on the cost of actually trying to manage that system. So clearly there's balance there as to whether it's worthwhile in certain areas. So as you said there, strategically, we can look at site-by-site basis and what's actually needed because of the noise that we see and what the actual area of concern is. Because obviously within tunnels, in London, for example, we're getting noise complaints because there's more developments occurring on top of where those tunnels are. Clearly, if the vibrations are going through the tunnel, through to the properties, we get councils knocking on our door asking for help to try and mitigate the noise. So we've got quite a few concerns that are developing, even though the railway's been there for hundreds of years before these houses have been built. We've still got to obviously accommodate that, unfortunately. So quite a few things there for us to think about, and the cost effectiveness of this is still to be looked at a bit more closely to how that would actually work. So looking at this, obviously looking at more numerical models is further work to look at how this can be developed and looking at how we can then take this by implementing it at field, by looking at how we can mitigate the noise and vibration on the slab track in particular through either a railhead repair, railhead maintenance, sorry, and maybe looking at the actual componentry from a pad point of view of how we can change the actual noise and vibrations that we actually have to deal with. That's a quick snapshot of how we can do that. Thank you very much.
And we move on to Iris, please.
Hello, everyone. We will continue with similar topic, mitigation of ground-borne vibrations. My name is Sérgio Class, first of all. This work was performed together with some colleagues also from the University of Porto. Some of them are here. Okay, as you already seen the previous presentation, the prediction and control of ground-borne vibrations and also noise represent significant environmental challenge for railway exploration in urban areas. When you look at this top figure, you can see that you are dealing here a very complex problem involving different parts with very distinct behaviors, and the dynamic interaction between them is not so easy to take into account. So we have to have a general numerical model to address all of these parts. In specific, the challenge in the work package 3 of this project involves exploring two distinct mitigation measures. First one, apply in the transmission path, where we apply an innovative solution based on the seismic metamaterial concept. And in a second mitigation measure, it's an application example of a mitigation measure applied at the receiver at the base isolated building. To deal with these both mitigations, we involve numerical modeling, advanced numerical modeling, and also experimental results. When you look at the first mitigation measure based on the seismic metamaterial concept, we can define a metastructure as a periodic association of individual structures, and the periodic characteristics of this system can produce a mitigation effect that in the acoustic field we call it a sonic crystal effect. This effect is responsible for the introduction of a band gap. This means that we can reduce the energy in a specific range of frequencies with the combination of or association of periodic or individual structures. We apply the same concept to the elastodynamic problems, and in the first phase we developed the mitigation based on numerical modeling, and in the second phase we go to the experimental test site and we build a small prototype, if you want, just to compare the numerical and the experimental results, and we have promising results for the next iteration. In the second mitigation measure, it is an application example, a base isolated building. It's a library located in Barcelona. We have the opportunity to perform different or some experimental works during the construction phase of this building, and with that results, the experimental results, we could calibrate a numerical model that takes into account the tunnel, the ground, and also the building. In specific, the supports of the building, that is a resilient material. And with that model, we are able to perform some analysis and evaluate some insertion loss curves. What happens next? Currently, we are developing an expedited tool for predicting ground-borne vibration levels in the structures located near to the track. Some of this work was already performed in the scope of the work package 4 in the In2Track3. The main result we're involving here machine learning techniques, and the main result will be a color map with vibration levels along the railway line. This methodology is adequate mainly for environmental impact assessment for the first stage of the project for a new railway line. Of course, we will integrate also the mitigation measures in this prediction tool. And the next we have right now we have a national project involving all other universities from Portugal and also in Spain, and we are trying to develop this new prediction tool. And that's all. Thank you.
Please, Urs.
This time I'm talking about reducing of noise after rail machining. The challenge is described on the next slide. Rail grinding is very beneficial for the surface quality of the rail. We can remove defects. We can also remove corrugation that can lead to substantial noise levels. But once the grinding machine is finished, it leaves behind a certain pattern on the rail surface that can be found to be quite annoying by line-side residents. So we tried to assess this reduction of noise levels. One of our supplier has developed a quite slightly different grinding technology in an unrelated project. And here we now wanted to see how big the effect of this optimization was. The results are on the next slide. We have here the four graphs. The two on the left are the rail roughness. So we have on the top the acoustic grinding and on the bottom the conventional grinding. The horizontal axis is quite strangely labeled in tons, and that's just the accumulated amount of traffic that has passed over the rails in between the measurement points. For this signal measurement here, this is a little bit unconventional, but this allowed us to compare measurements throughout our entire network, because when we compare the data in days, it's not always the same amount of traffic that passes over the rails. That is then confusing. That's why this is tonnage here, but it linearly relates with time. And we see the acoustic grinding does not cross the red line after grinding. The red line is the limiting factor that we have set by law in Switzerland. And the conventional grinding just jumps with one measurement point over this limiting line, and then after a few thousand tons or after a few days in time units, this is again reduced. We also tried to assess this effect in noise. That's the right set of graphs. Here we measured before and after. Also, the grinding event. 0 is grinding event, and the minus is before and plus is after grinding. And here we see that the effect is not that big. It can slightly be seen, but it's not that great. This is also in part due to the measurements that we have taken and due to the evaluation of those measuring samples. On the left, the roughness, we have a single value denominator that Switzerland uses. And on the right, with the noise graphs, we have the standard pass-by-noise measurements governed by ISO 3095. And now that's why our next steps on the next slide are that we want to develop measurement parameters from the spectral measurements that we have taken that quantify better the effect of these tonal noises. We have not assessed the tonal noise at all. There have been measurements made in parallel that we also would like to assess in the future. So now we just realized that in the study that we did, the saying is, if you can measure it, we can manage it. We could measure it, yes, but we did not take the correct evaluation methods to be able to manage these tonal effects after grinding very efficiently. And that's what we are going to do in the future. Thank you very much.
Thank you very much, Urs.
Yes, hello. My name is Astrid Pieringer. I'm a senior researcher at Chalmers University of Technology, and I will talk about the prediction and mitigation of curve squeal. And in this task, we have a part from Chalmers, which I will present, and a part from Luleå University of Technology. I'll start with a short introduction to curve squeal. So curve squeal is a highly annoying sound that occurs in tight curves. And it is so annoying because it's tonal and we deal with high noise levels. And the reason for curve squeal is imperfect curving. So the wheel set is normally under an angle of attack in the curve. So it cannot only roll, it also has to slide laterally to go around the curve. And this lateral sliding can serve as the energy input for self-excited vibrations that lead to squeal. And squeal is in several ways challenging. It's challenging to model because it's nonlinear and transient. It involves many different parameters. It is challenging to measure because it's rather chaotic than deterministic. And as a consequence, it's also challenging to mitigate. So in the part from Chalmers, we've mainly worked with modeling of curve squeal. We have a time domain model called VERAN for curve squeal, which deals with the high frequency wheel-well interaction. And in this project, we have extended the model to also capture transient effects. So now it can consider varying contact conditions during curving, such as creepages and the contact positions. And as it is a time domain model, it can not only predict squeal occurrence, but also squeal amplitudes. And then in the project, we've also connected the model to a commercial low frequency tool for vehicle track interaction. So this allows us to consider realistic curving scenarios from the start. And in simulations from that tool, we have seen that squeal occurs in a certain range of contact positions on the wheel tread, as you see in the figure to the left. So more towards the field side, we get squeal. But if the contact moves more towards the flange, then squeal stops. And that is something that you could use to develop mitigation measures. So if you have a measure that moves the contact position outside this squeal range, then this has potential to mitigate squeal. And one such measure could be an optimized rail profile that needs to be developed. And what will we do next? Well, we will use this tool more to research mitigation methods beyond friction modifiers. This will be done in a national project funded by Trafikverket, where we look at the influence of track design and track parameters such as rail pad stiffness. And this will be done in the European project Rail for Earth, where we will investigate the effect of geometry modifications of the wheel. And with this, I give the word to my colleague at Luleå University of Technology, Levi, who is online.
Hello, yes, this is Levi from Luleå University of Technology. In subtask 2, we looked at the specific real curve where we know that there's a squealing noise problem. It's located in Södertälje in Sweden. And we made a simulation environment of this curve in multi-body dynamic simulation, which is a low frequency simulation. So we cannot generate the squeal as such, but we can look at parameters that are known to correlate with high probability for squeal, such as high lateral creepage or sliding and high angle of attack of the wheel set. So the parametric studies in the simulation environment showed that track gauge does not affect curving significantly. However, track gauge does move the contact point on the wheel more to the field side, and as you can see from Astrid's presentation, this might increase the risk for squeal if the contact position is on the field side of the wheel. Then we could see that increased cant efficiency or higher velocity of the train improves the radial alignment of the train, so that we have a smaller angle of attack and therefore a smaller risk for squealing noise. And we could also see that longer boogie wheelbase increases the angle of attack. So if we have a train with different boogie types, the boogie type with the longest wheelbase is most likely the one that is prone to squeal for such train. And the simulation showed also that the highest angle of attack is right when the leading wheel set enters the curve, where we most likely have the highest risk for onset of squealing noise also. Can you take the next slide, please? Yes, this research will continue in the project Rail for Earth, work package 3, where we will look at curve squeal monitoring system. We will build this system in this specific location where we have made the simulations as well. And my own PhD project will continue also with curve squeal studies. For example, looking at how worn wheel and rail profiles affect the curving and risk for squeal. And I will also do field tests with friction modifiers. So thank you for your attention.
Thank you. And this concludes, I'm sorry, Sébastien is not going to say anything, but I thought he might be, so better safe than sorry. But this concludes our final event. I would like to thank you all for your participation, and I would also like to thank all those of you who participated online. It's been a pleasure having you. You will find all the presentations on the In2Track3 website. I will send an email telling everyone when it's there, so you know. You also find most of the video material that we have seen, you will find on the In2Track3 YouTube channel. So thank you very much. I close this session for now, and I will continue here in the room. Thank you.